The 14 moons of Neptune are a strange bunch. Most of them are small potato-shaped pieces of ice and rock. Some are so far away from Neptune that they need 29 years to circle Neptune once. Almost all of them are asteroids trapped by Neptune's gravity. 99.5% of all the mass around Neptune is concentrated in Triton. It's the 7th biggest moon and more massive than all other known moons in the solar system that are smaller than itself combined. Its surface area is about as big as the mainland of Russia and Australia together. Also, Triton is one of only 4 objects in the solar system that we know is geologically active. Triton orbits Neptune in the wrong direction, against the rotation of Neptune, which is unique in our solar system for an object as big as Triton. We can conclude from this that Triton hasn't always been a moon of Neptune, but probably was a dwarf planet that was forced into submission by Neptune when the solar system was younger and more chaotic. The most popular theory here is that Triton was once part of a double system. When Neptune migrated to the outer edges of the solar system, its gravity interfered with the double system and catapulted the other object into space, while Triton was forced into orbit. This would have disrupted the orbits of other Neptune moons rather violently and would most likely have either pushed them away from Neptune or let them collide or crash into Neptune. This would explain why Neptune's moons are so dominated by Triton. But this will end one day. Triton is being slowed down by Neptune, and eventually it will either crash into it or be ground by Neptune's gravity into a huge ring system similar to Saturn's. So don't buy real estate on Triton. You might be inside a black hole that's inside a black hole that's inside a black hole. Everything in existence could be black holes all the way down. It turns out black holes are much weirder than you think, and they break the universe much more than is usually explained, destroying time and space. And they may actually create infinite universes in the process. But before we can get to that, let's first build a black hole out of air. Everything can become a black hole if you squeeze it to a critical limit. You'd need to squeeze Earth down to the size of a coin for it to turn into a black hole. The Sun needs to be squeezed down to the size of a small city to become a black hole. And if a lot of mass is concentrated in a really tiny space, you get something super dense. This is usually how black holes are explained. Stuff becomes super dense and collapses into a black hole. But actually, you don't need any ultra-dense stuff to make them. We're ignoring some maths here, but all you really need to know is one thing. The larger black holes get, the less dense they are. So, really large black holes are kind of thin. A sun-mass black hole is only about 6 kilometers wide and has a density of about 1 Himalayan range per cubic meter. The supermassive black hole at the center of the Milky Way has a mass of 4 million suns, a diameter of 24 million kilometers, and a density of 6 blue whales per cubic meter. The ultramassive black hole IRAS 2100-4156 has a mass of 3.8 billion suns and is as wide as the solar system. But because it's so large, it is only as dense as air. This means, at least in theory, that if you take a gigantic balloon and fill it with undecillions of tons of air, the moment it gets to the size of a solar system, an event horizon suddenly forms and it turns into a supermassive black hole, without violence or squeezing. So now, let's think big. What do we need to make a black hole the size of the universe? A universe-sized black hole. The chunk of the universe that we can see from Earth is a sphere with a radius of 45 billion light-years, filled with hundreds of billions of galaxies, lots of gas, and a bunch of other things. If you add them up, it has the mass of about 1 million billion suns. Which sounds a lot, but on average, the universe is not very dense. If we break up all the galaxies, stars, gas, and energy and spread them equally inside the volume of the universe, we get an average density of about 5 hydrogen atoms per cubic meter. You can imagine this as the sort of ultra-thin cosmic air that makes up the universe. What would happen if we take a balloon as big as the observable universe and fill it with cosmic air? Well, it turns out that all the mass in the observable universe is more than enough to create a black hole. Actually, it's enough to make a black hole 10 times larger than the observable universe. But that can only mean one thing. We should be living deep inside a truly gargantuan, cosmic-sized black hole. There's one catch though. We know that our universe is expanding, and an expanding universe is not what you'd expect to see if you were inside a black hole. So our universe can't be a black hole, at least not in the naive way we've just described. Except there's a wild and mind-bending trick the universe could play on us. To find out how, let's jump into a black hole and die. A whole universe born inside a black hole. We usually imagine black holes as spheres with a singularity at their center, a point where all their mass is concentrated so much that our maths breaks down. But this is a lie. They are so much weirder. From the outside, a black hole looks like a normal black sphere, but the inside is where things stop making sense. Black holes warp the universe so much that at the event horizon, space and time switch their roles. Inside a normal sphere, space is finite, but time goes on forever. But inside a black hole, it's the other way around. Space goes on forever, but time is finite. So once inside, you see an infinite universe with no center. The geometry is too complicated, so we're simplifying. But basically, you could walk forever in one direction, or walk in another direction and arrive at the same place again. But not only that, inside a black hole time is finite, and it's now running out. So after a while, you start to notice that space itself is slowly changing. In one direction, space is being stretched, while in all other directions, space is shrinking. The whole universe is being squeezed, kind of turning into a collapsing spaghetti. Sooner or later, the whole black hole universe collapses into itself. All of space, every single part of it, is turning into a singularity. So the singularity of a black hole is not at its center or in any direction at all. It's in the future of whatever falls inside. We made a whole video about this if you want to learn more. So the singularity is not a place where you can go, it's an event in time that happens. Once it happens, you and everything else that fell inside the black hole will be mercilessly crushed into an infinitely small region with infinite gravity and infinite energy. Time, space, none of it matters anymore. Both kind of stop existing in ways that we would recognize. And then, is this the end? Well, maybe not. This collapse of the black hole universe into a singularity looks like one of the scenarios for the end of our universe, the Big Crunch, where long after the Big Bang the whole universe collapses into a singularity again. But if there's a big crunch, there might be a big bounce, like a rubber ball that you've squeezed too much and that suddenly rebounds. Space might expand again. So a new universe could be born inside a black hole. The funny thing about this scenario is that nothing has changed in the slightest outside the black hole. Watching from the outside, it's still a black sphere of nothingness, and yet on the inside, a new universe has been born. So maybe our universe was born like this, and we are all actually inside a black hole. But if our universe can also create black holes, they might give birth to new universes. Is our black hole universe also just part of a universe further up that's also a black hole inside another universe? Is there an end to it? Is there one original universe? Is the cosmos black holes inside black holes inside black holes? Infinite black hole universes. If the universe creates black holes that create universes, that then create new black holes that create new universes, this cosmic self-reproduction would be subject to natural selection. A Big Bang is a chaotic and messy event, so it's possible that the new daughter universes would not always be fully identical to their mums. Sometimes physics may be slightly different, with some fundamental values higher or lower, and so some universes might be able to create loads of stars, planets, and black holes. Others might not, maybe creating a uniform cosmic soup where no stars, planets, and black holes form. But if all universes are born inside black holes, in the long run all universe lines that don't create loads of black holes would die out. The universes with the conditions for loads of black holes would become the most common and spawn the most daughter universes. Survival of the fittest, but with universes instead of organisms. Our observable universe alone has created at least 10 to the power of 17 black holes so far. So maybe our universe has the physics and laws it has because it was born after a long process of cosmological selection that favored the production of tons of black holes. And that would have a lovely side effect. If universes are optimized to create as many new black hole universes as possible, they're optimized to create loads of galaxies and stars. And thereby also, by accident, the conditions for life to emerge. So universes that are the best at creating new universes are also the best at creating life. If this scenario is true, who knows how many bazillions of black hole universes might be out there, all with stars and planets potentially home to others like us. So, is our universe like this? The truth is we don't know. While these ideas are based on real science and work on paper, they're speculative and not testable. Also, cyclic universes don't actually explain why the universe exists in the first place or why it is the way it is. Instead of providing answers, these are really just new questions in disguise, so keep that in mind before getting too excited. But isn't it just wonderful and heartwarming that we're living in a universe where ideas as big as this one are even thinkable? There might be so much life. And if new universes are created constantly, maybe life will go on forever. Getting to space is hard. Right now, it's like going up a mountain on a unicycle with a backpack full of explosives. Incredibly slow, you can't transport a lot of stuff, and you might die. A rocket needs to reach a velocity of about 40,000 kilometers an hour to escape from Earth. To get to that speed, rockets are mostly containers for fuel with a tiny tip of payload. This is bad if you want to go to other planets because you need a lot of heavy stuff if you want to survive and maybe even come back. So is there a way to get to space with less fuel and more payload? A nice thing that solved most of our transport problems on Earth is what you call infrastructure. Whether it's roads for cars, ports for ships, or rails for trains, we've made it easier to get to places. We can apply the same solution to space travel. Space infrastructure will make getting into orbit and out to the Moon, Mars, and beyond easier and cheaper. Great, but what exactly is space infrastructure? Unlike an Earth space elevator, which is currently science fiction, there is a simple yet promising technology that does not require new science, magic materials, or huge investments, and that has been tested successfully in orbit already. A cable and a weight, known as a tether. The concept is so simple, it's surprising. What if we put tethers, hundreds or thousands of kilometers long, into space and had spacecraft use them as ladders to climb to higher altitudes and gain speed? This concept is known as the skyhook. It works even better if we make it spin. A counterweight holds a long cable in place while it rotates around a circle. A rotating tether slows down its tip relative to the ground at the bottom and speeds it up at the top like a catapult. This means that you can transfer energy from the tether and get a massive boost when released, more or less for free, equal to twice the tether's rotation velocity. Specialized fibers already exist that can survive the extraordinary stresses a skyhook would be faced with. To protect against cuts and collisions from debris and meteorites, we can thread our tether into a web of redundant fibers. Since our skyhook would pass over the same spot many times a day, this would allow small, reusable shuttles to catch up with it. Of course, it's not that easy. At its lowest point, the tether's tip is dashing through the atmosphere at around 12,000 kilometers per hour. Because of Earth's atmosphere, we can't lower the skyhook too much or it will get too hot from air friction. So it will dip to a height of 80 to 150 kilometers and no lower. To match this, we'll need specialized spacecraft that can get to the tether. While this isn't exactly easy, it's still much cheaper than getting a big tin can filled with rocket fuel to go 40,000 kilometers an hour. Catching the tip will be a challenge too. There's only a short time window of 60 to 90 seconds to find a tiny thing in the sky moving at Mach 12. To make this easier, the tip could have a sort of fishing line, a kilometer long, with a navigation drone that helps the spacecraft connect. Another challenge is keeping our skyhook in orbit. As more and more ships latch onto it and pull themselves up, they use up the momentum that keeps it in place. If we don't do anything, it will slow down and crash into the atmosphere. And here, we can cheat the universe a bit. The Skyhook is a battery of orbital energy. It's possible to balance the payloads coming in and being sent off. Arriving ships bringing humans and materials home to Earth add energy to the tether, which it can give to other ships departing into space. This way, the tether doesn't lose any energy. The more we use it, the cheaper it gets. If we're still losing energy with each boost, we can recover it with small electric or chemical engines that regularly correct the tether's position. A set of tethers, one around Earth and one around Mars, could make trips between the planets fast, straightforward and low cost compared to rockets. The Earth tether would sit in low Earth orbit to grab people and payloads and fling them off to Mars. The Mars tether catches them and slows them down for a landing on the surface. In the opposite direction, the tether could pick up a vehicle traveling through Mars's thin atmosphere at only about 1,000 kilometers an hour, not much faster than our airliners on Earth, and fling it back to Earth to be caught and lowered down. The tethers could shorten trips between both planets from 9 months down to 5 or even 3, and reduce the scale of the rockets required by between 84 and 96%. Even better, people may be able to travel in relative luxury, as we could afford to invest in passenger comfort. Tether travel would be first-class seats to Mars. Together, tethers around Earth and Mars could provide the rapid and cost-efficient transportation backbone that would make space travel affordable. But let's go further. Starting from low Mars orbit, a tether could boost ships to the asteroid belt. The first craft sent to a new asteroid would need rockets to slow down at its destination. Subsequent arrivals might find a tether waiting to catch them and send them back for free. Getting to asteroids cheaply is a major factor in opening up the resources of the solar system. Precious metals and valuable minerals could be delivered to Mars just weeks after they were cut out of their asteroid. They would be the perfect building blocks for our interplanetary civilization. But why stop here? Mars moons are very convenient. No other moons in the solar system orbit that close to their planet. Phobos is so heavy that we don't need to worry about slowing it down, making it the perfect attachment point for super tethers just under 6,000 kilometers long. The lower tip would fly just over the surface of Mars and be very easy to catch. The upper tip can fling ships all the way to Jupiter and Saturn. The same super tether can also bring the inner solar system closer. Venus and Mercury are a single swing away. Unlike Mars, they're bursting with solar energy and are rich in minerals. In the long term, nothing is stopping humanity from constructing a zero-propellant transport network for the terrestrial planets centered on the Martian moons. Tethers are a comparably cheap and sustainable solution to making space travel affordable and the rest of the solar system accessible for exploitation and exploration. Considering that we have the technology to build them today, there's really no good excuse to wait any longer. Parts of the solar system are far away, but they could be very close. Absolutely everything you think about yourself and the universe could be an illusion. As far as you know, you are real and exist in a universe that was born 14 billion years ago and that gave rise to galaxies, stars, the Earth, and finally you. Except, maybe not. You may actually not exist for real, but be the dream of a dead universe. You and everything you think exists. Crazy as it sounds, this may be an unavoidable consequence of our best scientific theories about the universe. Okay, this is a bit much. Let's start at the beginning. We need to understand 3 concepts for this idea to make sense. 1. The arrow of time. What distinguishes the past from the future? Put a drop of red ink into a glass of water, and you see the ink spread until it fills the container, but never the opposite. Colored water where ink spontaneously concentrates and becomes a drop at the surface again. Time always seems to flow in the direction in which the ink spreads. But if you take a microscope, all you will see will be a swarm of molecules colliding at random. There are no rules, no forwards and backwards. Every individual motion that happens can occur in reverse. But we perceive a sort of arrow of time that makes things happen in one direction. How does this phenomenon occur? Well, this arrow of time is not actually fundamental, but a matter of probability. When ink molecules spread to fill a glass, there are many different slots of space they can occupy, and therefore many different possibilities to combine them. And just like your chances of winning the lottery grow the more tickets you have, the probability that ink molecules will end up filling the glass is much higher than the probability that they'll concentrate in just one spot. So it's not that the ink forming a drop again is forbidden by the laws of physics, it's just extremely unlikely. To see it, you'd have to wait about 10 to the power of 100 sextillion years, a 1 followed by 100 sextillion zeros. If you had this much time to spare, eventually, by pure random chance, you'd see a red blob form again. Actually, with enough time, you could see any shape forming, like, for example, a small, red, soggy brain. Okay, let's move on to idea 2. 2. The far future of the universe. Our universe was born 14 billion years ago in the Big Bang. It expanded and evolved to give rise to the myriads of galaxies and things. In other words, the universe is kind of a glass of water with a lot of ink doing stuff. It has an arrow of time. But the universe is not a static glass, it seems to be getting bigger at an ever-increasing speed because of dark energy. Basically, everything in it is getting more and more diluted. In about 100 trillion years, the last star will die. Then, few interesting things will happen for the next few decillions, vantillions, and googles of years. Eventually, the universe will be a dark place fully dominated by dark energy, a rapidly expanding ball of pure space almost devoid of matter. You might think that this would lead to the ultimate death of everything, but dark energy has one last surprise for you. In a universe dominated by dark energy, space expands so dramatically that it creates a cosmic horizon around you, a border beyond which nothing will ever be able to reach you, not even light. So for every practical purpose, the universe has become a glass of finite size about 36 billion light-years wide, surrounded by an impassable cosmic horizon. Such a universe glass is basically a giant black hole turned inside out. We know that due to quantum effects, all black holes emit a tiny amount of particles, a phenomenon known as Hawking radiation. And so does our inside-out black hole. In the end, this radiation will fill the universe glass with particles again. At this point, so far in the future that giving you a number has no more meaning, we've reached the true final state. The universe has now become a closed box full of particles at an extremely low but finite temperature. And since they have a temperature, they undergo random motions. Or in other words, a glass filled with water and ink and an infinite amount of time ahead. Things are about to become interesting again. 3. Typing monkeys and fake universes. Eternity is a long, long time. So now, even the most extremely unlikely things can happen. The fluctuating particles are bumping into each other over and over and over again, creating every combination of particles that's possible. They're like a monkey typing at random on a typewriter. Almost all of the time it types gibberish. But with enough time, eventually it will write the first acts of Hamlet. And with even more time, the complete works of Eminem. If ink in our universe glass generates any random arrangements of particles, what could they be? Well, a spontaneous fluctuation could give rise to a planet, or to a galaxy, or even to a lot of them. So maybe our universe has already ended, and all we see around us is a pop-up universe. Not a universe that evolved from a Big Bang, but one that fluctuated into existence by pure chance. And that, like the drop of ink, will only exist for a while before dissolving again. Being random, pop-up universes could be similar to ours but with funny glitches. In some of these universes, dinosaurs are riding snails. In another, stars are made of blueberries. In another, you're wearing a funny hat. Scientists in such universes wouldn't understand those glitches, so maybe the greatest mysteries of physics are just nonsense bugs of our pop-up universe. But not all possible fluctuations of our dead universe have the same probability of occurring. Smaller fluctuations are much more probable than bigger ones. A planet is more likely than a galaxy. But you know what's even way more likely? A human brain. Are you actually just a brain? You think, therefore you exist. But what else do you truly know? In the end, your brain is just interpreting signals from your senses and creating a world that you experience. So technically, you could be just your brain that thinks the world is real. And if we follow the logic of the ink in the universe glass, in particular, you could be a disembodied brain that, just by chance, emerged in a dead universe with your complete set of knowledge and memories. This is a pretty bizarre idea, but if we do the maths, it's kind of pretty solid. Let's compare the number of brains inside bodies in a living universe with the number of naked brains in a dead universe. Let's go really big and imagine that a total of 100 quadrillion humans will live around Earth. and that the same amount of people will live around every star in the universe. If we add this together, we get about 10 to the power of 41 brains inside bodies that will exist. However, in a dead universe that has had enough time to explore all possible fluctuations and that will exist forever, the number of naked brains that would emerge is, well, infinite. So the probability that you're a floating brain is not only vastly larger than the probability that you're a real human, it's so inconceivably larger that we can't even meaningfully quantify the difference. How do you compare a number to infinity? So, are you a floating brain that exists for one moment in time, then basically forever passes, and then you exist for another moment in time? Maybe not even in that order. Maybe your life happens backwards and you just don't notice. Maybe you've lived trillions of times already. Are you the dream of a dead universe? Really? Like, really? Well, probably not. First of all, there are a few loopholes. For example, dark energy could behave completely differently from what we think today and lead us to another future. Or maybe our dead universe will be too motionless to allow the creation of brains, even with infinite time. Or maybe the universe will end up dying in another way. Our understanding of the cosmos doesn't have a solid enough foundation for anyone to worry if they're real or not. Loopholes aside, if you were a fluctuating brain, all the laws of physics stored in your brain would have originated at random and shouldn't bear any relation to the real world. But we just used those laws to prove that you're a floating brain. So even if you believe that you are a floating brain, you'd have to admit that you have no good reason to believe that you are actually a floating brain. Okay, so this hallucinatory trip might teach us something about our theories about the universe. But in the end, it's just a really weird exercise in what you can do with physics. An exercise of what brains and bodies are able to think about. So don't worry, you're not a dream of the dead universe. Probably. A 3-story building is about 10 meters tall, 6 times bigger than you. In the opposite direction, 6 times smaller than you get things like a cute squirrel, about 27 centimeters small. So the building is just as big relative to you as you are to a squirrel. You're in the middle. It's easy to understand. In fact, you are in the middle of everything in the universe. Let's go on a fantastical journey together to the small and the large and see if it's really true. An A320 is 37 meters long. The roofer's hummingbird is around 7 centimeters. Both of these flyers are 23 times bigger or smaller than you, and both fly intercontinental distances. The tiny bird migrates between Alaska and Mexico. If the hummingbird were the same size as the jet, it would circle the Earth 85 times every year. Dinoponera, the largest ant in the world, is about 55 times smaller than you. Their small colonies have around 100 individuals but no queens. Instead, they ruthlessly compete for status within the nest, which can reach 1.2 meters deep. If humans lived like Dinoponera, we'd be building towers of over 25 stories filled with offices and ruthlessly competing for status. And wait. The deadliest and most annoying insect in the world is the mosquito, 235 times smaller than you, while on the other end, the Empire State Building is about that much larger than you. Kind of unimaginable how something this small creates so much devastation for something that big. We're getting to the borders of human perception now. Like coarse grains of sand about 3 millimeters, 550 times smaller than you. You can feel their shape and roughness between your fingers, and if you focus, see them individually. We mix them into concrete that can hold up the tallest towers ever built, like the 828-meter-tall Burj Khalifa that's 500 times larger than you. If you were that tall, people would be as small to you as grains of sand in your hand. Hey, be gentle. Anything smaller or bigger, and it becomes hard to grasp. A medium-sized city like Lisbon is about 6,000 times larger than yourself and permeated by a network of highways, roads, and alleys. On the other end, about 6,000 times smaller than you, are your small arteries permeating your whole body. Actually, you're in the middle between your network of blood vessels and the network of a city like Lisbon. If you think of a city as a living being, you find more and more parallels. A small alley is as small to the city as an arteriole 0.1 millimeters wide is to you. Your tiniest capillaries are to you what the pipes bringing water to homes are to Lisbon. Going further, 100,000 times smaller than you, we reach a typical skin cell about 30 micrometers in diameter. A neutrophil is half as big, and one of your red blood cells is merely 7 micrometers. They are as small to you as you are to the entire Tokyo metropolitan area, the largest urban area in the world spanning over 160 kilometers. You are so incredibly big, filled with so much complexity, so many different moving parts. Or are you just a cell in the human civilization's superstructure? Are you both? Our steps are getting larger and larger now. Germany is around 875 kilometers from north to south and the fourth biggest agricultural exporter in the world. Rhizobia is a nitrogen-fixing bacteria up to 3 micrometers long, and without it, that sort of agricultural production is impossible. So we have a country and a bacterium depending on each other, and you are in the middle, both being roughly 550,000 times larger or smaller than you. What about the whole Earth? It's about 12,700 kilometers in diameter, about 7.7 billion times larger than you. On the other side of the scale is Corynebacterium, as little as 0.3 micrometers across, living on your skin and eyes along with 100 billion other bacteria, more than 10 times more than there are humans on Earth. Again, you're in the center, right in the middle of something so large that our civilization is a mere scratch on its surface, and something so small and numerous you never notice its presence even as it touches you. Does that make you feel small or big? From here on out, your brain is breaking a bit. 4 times wider than Earth is Neptune, a cold blue gas giant 49,500 kilometers wide. The largest planet, though, is Jupiter, 140,000 kilometers in diameter. A titanic abyss shrouded in terrible winds. You could drop Earth whole into its depths and it would simply vanish. On the opposite scale, we find the deadly West Nile virus, 50 nanometers in diameter. Or one step down, the spike proteins on a coronavirus that open up cells for its RNA payload. They are as small to you as you are to the planet Jupiter. You are in the middle between gigantic planets and the world of viruses. These tiny things. So deadly. Let that sink in. A tiny virus is taking over and killing lung cells up to 500 times larger than itself with the help of a tiny protein weapon. That's like you trying to kill a giant the size of the Burj Khalifa with a screwdriver. But the real boss of the solar system is the Sun. 10 times bigger than Jupiter, a billion times larger than you, controlling all the planets and source of all energy that drives life. A billion times smaller than you, clearly the boss of our body, is a DNA strand containing all the information making your life possible. You're right in the middle between the most important factors keeping everything alive. From here on, things just kind of stop making sense. A billion is already too much, but now everything just seems to mean a lot. The supermassive black hole at the center of our galaxy, Sagittarius A star, is 14.5 billion times bigger than you. A hydrogen atom is 15.5 billion times smaller than you. Yeah, okay, sure. But the thing is, we're not even close to being done, and it's not impossible to get at least a sense of how these scale. The solar system is 22 trillion times larger than you. On the other end of the scale is the wavelength of low-energy neutrinos released from fusion reactions in our Sun. About 100 trillion of them are passing through you every single second, like ghosts a trillion times smaller than you, basically never hitting any of the particles inside you. If you moved through the solar system in a straight line, you probably wouldn't hit anything either. Although things are beginning to get really weird now. A single proton at the heart of the hydrogen atom is almost exactly 1 quadrillion times smaller than you. If the proton were as big as you, the hydrogen atoms would be taller than 12 Mount Everests. On the other end, we meet something that just breaks human brains, the incredible vastness of space. We just have no reference for these distances at all. The distance to the closest star to Earth, Alpha Centauri, is not 1 quadrillion times in the other direction from the tiny proton, but 24 quadrillion. Space is just so large, it's kind of mean. And it goes on like this. A quintillion times smaller than you is the strange world of the quarks. The proton is not actually like a tiny ball, but kind of just a ripple on the surface of the ocean of quarks. Every moment, countless quarks pop into existence along with their antiparticle enemies before doing furious battle and annihilating each other in an instant. How many? Impossible to say, because the harder you look for them, the more quarks seem to appear. We're simplifying so much it's like a lie anyway. However we choose to illustrate this, it's wrong. What actually is a quark? What does it look like to human minds? Nobody knows. As you sit here confused, let's look up again. The ocean of quarks in a proton inside a single atom of a single cell of your body is as small to you as you are compared to a sphere around 174 light-years across, containing about 16,000 stars. And this is just a tiny speck of dust to our galaxy. The Milky Way is close to 1 sextillion times larger than you. At the opposite end, we have particles a sextillion times smaller than yourself, like the wavelength of high-energy neutrinos released when cosmic rays hit our atmosphere. We're getting to the end. The observable universe is 93 billion light-years in diameter, close to a billion human lengths. But it's still finite. It's only 465,000 Milky Ways side by side. If you were the size of our galaxy, the observable universe would only be a day's drive across. On the other end of that scale, we have the tiniest particle ever detected, a proton traveling so close to the speed of light it got squished into a pancake. As small compared to you as the whole observable universe is big to you. We're at the border of things that we have evidence for. Are you truly in the middle of everything? The theoretical smallest physical distance is the Planck length, 100 million times smaller than even the pancake proton. But we don't know if it's real, only that our theories of the universe break down here. Likewise, on the other end, does the bigness of the universe match the smallness of the Planck length? Well, actually, the universe could be considerably larger than that, but we will never know. Let's go back and look at the dimensions again. There are so many big things and so many small things wrapped up in them. The universe seems to be exactly the right size, with you in the middle. Humans can survive in this universe as long as we have an energy source. Unfortunately, the universe will die. It will happen slowly, over many billions of years, but it will happen. On a universal timescale, stars like our Sun will be gone in no time. Luckily, there are places that will exist practically forever from a human perspective. The corpses of dead stars. White dwarfs. They could be humanity's last home right before the death of the universe. What are these strange things, and what happens when they finally die? How long stars live varies drastically, depending on how massive they are. For example, really massive stars burn hot and fast, dying violently in supernova a few million years after birth. But they're the exception. 97% of all stars will end their existence as white dwarfs. There are two ways this can happen. Small stars, so-called red dwarfs, burn out over trillions of years until they eventually quietly turn into white dwarfs. Medium-sized stars like our Sun are more interesting. Imagine the Sun as a huge pressure cooker that fuses hydrogen into helium in its core through its gravity. The fusion of elements releases extreme amounts of energy that pushes outwards and stabilizes the star, keeping it in a delicate balance. When the Sun is old, the hydrogen in the core is exhausted, and the Sun will begin to burn helium into heavier elements. While doing so, it will shed its outer layers. When this process is over, more than half of the Sun's mass will be lost into space as a spectacular planetary nebula millions of kilometers across. What remains will be its former core. A white dwarf is born, a star corpse. While its former self was about 100 times its diameter, now it's only about as big as Earth, but still with about half of its former mass. This means it's extremely dense. A teaspoon of white dwarf is about as massive as a car. Its surface gravity is over 100,000 times higher than Earth's. If you tried to land on it, you'd immediately be compressed into a steaming puddle. Life around a white dwarf is very unlikely, but possible. Most of them that exist now were former stars that, well, died, which probably ruined any planets they once had. But that's not all. Since they are so small, a planet would need to orbit them about 75 times closer than Earth is to the Sun to have liquid water. This proximity has up and down sides. For one, it would tidally lock the planet, giving it a permanent day and permanent night. At the edges of these day and night zones, life could be possible. But white dwarfs have a very stable energy output, so they might actually be safer to live around than many red dwarfs. This is still speculation at this point, but if we could find a white dwarf with the right conditions to settle around, we could have a home for many billions of years. But why do they shine so much longer than other star types? White dwarfs are very, very hot, up to 40 times hotter than our Sun, ranking among the hottest objects in the universe. But they are not incredibly active. All the heat inside of them is trapped and has nowhere to go. Only on its outer layer can it escape into space. But space is mostly empty, so heat can't be transferred by conduction. The only way energy can escape is by radiation. This is so inefficient that white dwarfs will take trillions of years to cool down, which may make them humanity's last refuge. They might be the last sources of light and energy in a dying universe. According to some estimates, white dwarfs might shine as long as 100 billion years, 10 billion times longer than the universe has existed. So far into the future that no regular stars will shine anymore. Galaxies will have evaporated. And only then will the first white dwarf turn into the first black dwarf. When this happens, the last hope for life will die off. Black dwarfs will be inactive spheres with no energy left to give. Still massive enough to kill you if you get too close. So cold that they'll be near the coldest possible temperature in the universe. So dark that they are practically invisible. The universe will enter its last stage, heat death, which will leave the universe unrecognizable. An absolutely dark and cold graveyard with black holes and black dwarfs scattered over trillions of light years. We don't know for sure what will happen with black dwarfs in the end. If the proton, one of the fundamental parts of atoms, has a limited lifespan, black dwarfs will slowly evaporate over many trillions of years. If the proton does not decay, black dwarfs will probably turn into spheres of pure iron via quantum tunneling over a time span so obscenely gigantic that calling it forever is okay. These iron spheres will then travel completely alone through a dark universe. Nothing new will happen anymore. Forever. While this may sound kind of dark, this is so far away that for our purposes today, it might as well not happen at all. It doesn't matter what happens in a billion trillion years. Right now, we happen to exist at an excellent time, able to be in awe about a universe filled with endless stars and light and planets, and enough time to visit them one day. The universe is going to die one day. But how? Well, it turns out our cosmic fate will be decided by a fight between two titans. The two warriors deciding the fate of the universe. Our universe was born 14 billion years ago in the Big Bang and has been expanding ever since. For some reason, new empty space is being created out of nothing between galaxies. Space itself is becoming bigger. Will it go on forever, or will it stop one day? Today, we think the universe is at the mercy of two cosmic demigods fighting for dominance. The first one is all the stuff in the universe: galaxies, gas, dark matter. While they're very different, they just want to do one thing: get together. Matter is attracted by matter, pulled together by gravity. And gravity also pulls on the universe as a whole, slowing the expansion that started at the Big Bang. Our second warrior is empty space. While it seems, well, empty and powerless, empty space has an intrinsic energy. We don't really have an idea what this energy is or why it's there. It's really a placeholder that fills a blank in our understanding of reality. But it's got a cool name: dark energy. Dark energy pushes things apart, a sort of anti-gravity that accelerates the cosmic expansion. So we have all the matter in the universe pulling in and empty space infused with dark energy pushing out. Whoever wins will kill the universe in fun ways. But who will win? It all depends on the mysterious dark energy. Will its strength stay the same, a common assumption just because it keeps our models simple? Or will it get weaker? Or will it get more powerful over time? 1. Constant dark energy, heat death. If the strength of dark energy stays constant, it will win the war. Since space is growing, matter is getting more and more diluted, like sugar in a cup being filled with more and more tea. But as the universe expands, new empty space is created, which brings more dark energy, which pushes everything apart even more, which creates more empty space, which makes the universe grow even faster. A feedback loop that will make the universe expand at an exponential rate. Every 12 billion years or so, it will double in diameter forever. But while dark energy is winning the war, matter is winning at least one battle. At short distances, it can keep things together. Local galaxy bubbles can overcome the push of dark energy. In a few billion years, our local group of galaxies will merge into a gigantic ball with trillions of stars. It will soon become our last view of the cosmos. All other galaxies will be pushed away by the expansion. For us, it will look like the rest of the universe is rushing away, until in a few 100 billion years, we won't see other galaxies at all. We'll be alone, surrounded by a seemingly infinite dark void. In about 100 trillion years, all the stars of our supergalaxy will have died out. All gas that could create new stars has been consumed, and no new gas can come in. The galaxy will be dark and filled with stellar corpses. Over quadrillions of years, white dwarfs and neutron stars will slowly cool until becoming truly dark, turning off the last lights of the universe. All structures, big and small, will slowly dissolve. One by one, all dead stars and planets will leave the supergalaxy, which slowly dissolves over sextillions of years. Every object will end up on its own, which means that dark energy takes over again, creating more and more empty space between everything. Objects will be so far apart that it will be as if each had a universe for itself. Not much happens anymore until in a googol years, all black holes will have evaporated. In the end, entropy and dark energy won't stop until their job is finished. Over time spans you might as well call forever, all remaining structures might even dissolve into single particles that will be pushed away from each other by an ever-growing empty space. Imagine a whole universe with just a single lonely particle traveling through nothingness. This is the final state, the true end, the big freeze, or heat death. A completely featureless, cold, and eternally expanding universe. Nothing will ever be able to happen again. Forever. Phew, well, that was a bummer. What else could happen? 2. Increasing dark energy. Big rip. What if dark energy gets stronger? In this case, empty space won't just win over matter, it will literally rip it to pieces. In the Big Freeze scenario, matter lost the war but won some battles. But here, matter wins nothing. Dark energy is growing stronger over time, overcoming the pull of gravity and creating new empty space at smaller and smaller distances. In this scenario, things will escalate quickly. It could start as early as 20 billion years from now. First, dark energy will create empty space between individual galaxies. Our galaxy will leave its local cluster and begin to drift alone in a rapidly inflating and ever darker cosmos. Some billion years later, empty space starts to push between individual stars, dissolving the galaxy. If you live on a planet in a star system, the night sky will start looking sad and gloomy, as other stars are pushed too far away to be seen. A few million years after the sky turns dark, dark energy starts to create empty space inside star systems. Your planet is pushed away from its star, and all life in the universe freezes to death. There's not much time left, as a few months later, dark energy is creating empty space inside solid objects. Stars, neutron stars, planets, asteroids, everything solid is being ripped into pieces. If you're on a spaceship, you only have a short time before you are ripped apart. Half an hour later, even atoms are destroyed as new space is being created so furiously that electrons and nuclei are separated. Now the universe has just a fraction of a second left. In this final moment, only dying black holes remain, drained and defeated by dark energy. They're tiny, septillions of times smaller than an atom, and they explode with the power of a trillion supernovae in a trillionth of an octillionth of a second. Finally, the very fabric of reality is torn to its core, obliterating space-time itself. The Big Rip. Space and time have lost their meanings, making it impossible to predict what will happen next. 3. Decreasing dark energy. Big Crunch. Poor matter. But there is one scenario where it wins. If the strength of dark energy decreases with time, and if this reduction is strong enough, the pull of gravity will win and all the things in existence will move towards each other, unfortunately making the universe collapse into itself. No one knows when this might begin, but it could be as soon as a few 100 million years. What will it look like? As the universe begins to contract, over billions of years, galaxies and galaxy clusters approach each other until they eventually collide. They're mostly made of empty space, so a collision is like the gentle merger of two clouds. At any rate, first galaxies and later individual stars get closer and closer. As the universe goes on collapsing, you might worry about stars and planets eventually crashing against each other. This will happen, but it's not your worst problem. If space itself shrinks, this also concentrates all the radiation emitted in the past by all the stars, supernovae and quasars that ever existed. Now, empty space is filled with radiation. The dark nothing between stars is heating up, making life unpleasant and then impossible as planets just burn. Slowly at first, then rapidly, space gets as hot as it was after the Big Bang. Stars are pretty hot, but now the space around them is hotter. They're literally boiled from the outside. As the universe collapses into itself, all galaxies and all stars merge into a single ball of hot plasma. The Big Crunch is complete. From here on, there are two possibilities. Either the universe will collapse completely into a singularity, a point of zero size and infinite density without space and time, the way it might have been before the Big Bang. Or the universe could bounce back, restarting the cosmic expansion, creating a new baby universe. Somewhat poetic, really. Everything died, but everything is reborn. But to be clear, we have zero evidence that this has happened before or will in the future. So what will happen? Most scientists think that dark energy will stay constant, so the likely fate of the universe is heat death, eternal cold, and utter boredom. Which seems sad, but has a huge upside. In this scenario, we get to have the universe for the longest. It gives us trillions of years to expand, jump from star to star, maybe even from galaxy to galaxy. We might even find a way to keep consciousness around forever. We don't know. So we just have to wait and see, and make the most of the amazing universe we have right now. The universe looks like a vast empty ocean sprinkled with rare islands of galaxies. But this is an illusion. Just a small fraction of all atoms are found in galaxies, while the rest is thought to be drifting in between, in the intergalactic medium. Like the roots of some massive tree, gas spreads out from each galaxy, gravity funneling fresh mass into this dense cosmic forest. Here in the intergalactic medium are the raw materials of creation: hydrogen and helium, woven into sheets and filaments that flow into galaxies where they eventually create stars. But if we look closely, we see who's actually in charge: quasars, the single most powerful objects in existence. As small as a grain of sand compared to the Amazon River, they reside in the centers of some galaxies, shining with the power of 1 trillion stars, blasting out huge jets of matter, completely reshaping the cosmos around them. They're so powerful that they can kill a galaxy. What are they, and how do they mold the structure of the universe at their whim? Everywhere you look, weird things in the sky. In the 1950s, astronomers noticed mysterious loud radio waves coming from spots all over the sky. They were named quasi-stellar radio sources, or quasars, because they were dots like stars but were seen in radio waves rather than visible light. Everything about them was strange. Some flickered, others emitted high-energy X-rays in addition to radio waves, but all seemed to be tiny. They all moved extremely fast, as much as over 30% the speed of light. The only explanation was that they must have been so distant that their apparent speed was actually the expansion of the universe moving them away from us. But these enormous distances meant that quasars couldn't just be stars, but the active cores of galaxies billions of light years away. And it gets crazier. To appear so bright and loud, given these vast distances, they are thousands of times brighter than the entire Milky Way. Monsters exploding and screaming into the void with a violence not thought possible before. As we mapped the sky, we discovered over 1 million quasars, and they all seemed to be very far away. Looking into space far away means very long ago, because light takes so long to reach us. Quasars were common in the early universe, having peaked in number 10 billion years ago when galaxies and the universe itself were still very young. Let's go back in time just 3 billion years after the Big Bang and see what was going on back then. The incredible power of quasars. How could an early baby galaxy be so incredibly bright and violent? All that light and radiation couldn't be stars, as there weren't nearly enough of them. And since galaxies tend to grow with time by merging, the starlight from small galaxies shouldn't be far brighter than any galaxy today. There's only one way to generate the vast amounts of energy a quasar shines with: feeding supermassive black holes. We still don't know how exactly they formed, but it seems that every galaxy has one in their center. But how can the brightest things in the universe be black holes which trap anything and everything that crosses their event horizon? Well, the light of a quasar is not coming from inside these black holes. Rather, it comes from the space around them, a massive orbiting disk of gas called an accretion disk. Quasars use the same fuel as stars to shine: matter. It's just that black holes are the most efficient engines for converting matter into energy in the universe. The energy released by matter falling into a black hole can be 60 times greater than that released by nuclear fusion in the core of a star, because the energy released by a black hole comes from gravity, not from nuclear reactions. Matter falling into a black hole speeds up to almost the speed of light before it crosses the event horizon, buzzing with an incredible amount of kinetic energy. Of course, once inside the black hole, it takes that energy with it. You only get to witness this energy if you drop your matter in the right way. Fall straight down and the outside universe gets nothing. But when you have a lot of matter, it spirals in incredibly fast towards the event horizon, forming a disk. Collisions between particles and friction heated up to hundreds of thousands of degrees. In a space not much bigger than our solar system, the core of a galaxy can release many times more energy than all its stars combined. This is what a quasar is: a supermassive black hole having a feast. And these black holes eat a lot. Typical quasars consume 1 to 100 Earth masses of gas per minute. 10 billion years ago, the universe was about a third of its current size, so the intergalactic medium was much less spread out, meaning the filaments of gas around quasars could feed them a banquet, making them vomit insane amounts of light and radiation. The brightest quasars power jets, tangling the magnetic field of the matter around them into a narrow cone. Like a particle accelerator, they launch enormous beams of matter out, plowing through the circumgalactic medium, forming plumes of matter that grow to hundreds of thousands of light-years in size. It's almost unfathomable in scale. A tiny spot in a galaxy carving out patches of the universe hundreds of thousands of light-years long. But quasars can't eat for long, maybe a few million years, because their feast ultimately kills their galaxy. How quasars kill galaxies. Okay, maybe killing is a bit of an exaggeration. A galaxy is still there after its quasar turns off, but it will never be the same again. Quasars, being among the hottest and brightest things in the universe, break their galaxies by heating them up too much and stopping star formation. Stars are gas that collapsed in on itself and then got really hot. But in a cloud of gas that's already hot, atoms are moving quickly. When they collide, they hit hard, exerting pressure that resists gravity's squeeze. So hot gas cannot form stars. Instead, the best gas for forming stars is already cold and won't put up a fight when it's time to collapse into a star. On top of that, quasars push gas out of their galaxies. Not only does this starve the quasar, but its galaxy loses the raw materials for new stars. As sad as this sounds, it might be a good thing for life. The alternative can be far more dangerous: too many stars. New stars forming is usually followed by massive stars exploding in supernovae, so planets would be burned sterile. But of course, it's more complicated. Like the intricacies of our own planet's biosphere, every piece of the galaxy is dependent on and influencing every other part of the galactic environment. While hot things like quasars and supernovae tend to push gas out of the galaxy, shockwaves and quasar jets can also compress gas, making new stars at least for a short time. But in general, we can say that without things becoming a bit more chill, we would not exist today. Which brings us to our final question. Did the Milky Way have a quasar in the past? It's unclear if every galaxy went through a quasar phase, but understanding distant quasars may provide clues to the history of the Milky Way. Galaxies don't do a good job of preserving their history. Like sand on a beach, the endless churning mixes away the clues to their past. It's possible the Milky Way was once a quasar, which may have allowed our supermassive black hole Sagittarius A star to have grown to 4 million times the mass of the Sun. And as dormant as it is now, Sagittarius A star could turn into a quasar in the future. In a few billion years, the Milky Way will merge with Andromeda. We've seen over 100 double quasars in galaxies smashing together, where fresh gas is provided for the central black holes. But it won't last for long. When galaxies merge, so do their supermassive black holes, sinking into the center of their new galaxy, kicking up dust and stars in every direction. We don't know whether this will happen, but it would truly be an incredible sight. Maybe some beings in the far future are going to witness it and be in awe of what they see. Black holes are the largest collections of pure, violent energy in the universe. If you come too close, they'll devour you and add your energy to their collection. And so the energy is lost to us forever. Or is it? It turns out there's a universe cheat code. A way of powering civilizations until the very death of everything, or of constructing the largest bomb in the universe. But how? Didn't we learn that all energy is trapped forever in black holes, even light? This is true. Everything you think you know about the weirdest thing in the universe is about to get weirder for one simple reason. Black holes are spinning. Why black holes spin? When really massive stars die, their cores collapse under their own gravity into black holes. This means something very big becomes very tiny. Like the tiniest anything can be in this universe. But stars are rotating, and a fundamental property of our universe is that things that are spinning don't want to stop spinning. We call this angular momentum. And this angular momentum can't go away. A big thing that spins and becomes smaller spins faster. So, as the core of a star collapses, its momentum makes it spin faster and faster and faster until it collapses into a black hole. And the black hole keeps on spinning, inconceivably fast. Some of them spin millions of times a second. Why spinning black holes are special? Just like non-spinning black holes, spinning black holes have an event horizon and a singularity at their core where all of their mass is concentrated. The singularity is usually described as a single, infinitely small point with no surface area. But points can't rotate, so a rotating singularity can't be a point. Instead, it's a ringularity. A ringularity is a ring with a thickness of 0 and no surface, spinning extremely fast, containing all the mass of the black hole. The black hole is spinning so fast that it morphs space and time itself. It literally drags space with it, such is its power. This creates a new and super weird region of space-time, the ergosphere, which envelops the black hole. If space and time are completely broken inside the event horizon, then they're only half broken inside the ergosphere. Inside the ergosphere, nothing makes sense. It's possible to enter it and then leave it again, but it's probably not a great experience. You can imagine it like this. Falling into a static black hole is like sliding down a hole. Being inside the ergosphere of a spinning black hole is like spiraling down a deadly drain. The black hole transfers its own kinetic energy in the form of rotation to everything that enters the ergosphere. The ringularity makes you dance whether you want to or not. You need to move faster than the speed of light just to stand still here, which is impossible. But here's our cheat code. We can steal this energy. And there's a lot of energy to steal. How to steal energy from a monster. Take the supermassive black hole at the center of the Milky Way. We could steal as much energy from it as every single star in the Milky Way emits in 1 billion years combined. The easiest way to steal this energy is, oddly enough, to drop something into the black hole. We've seen that the ringularity forces energy on us when we enter the ergosphere, which is a lot like being in a whirlpool with space-time rushing around and around. If you're clever, you can use the water to your advantage and swim faster than before. In practice, this means sending a rocket into the ergosphere and making a trade with the black hole. We give it some mass energy and it gives us some of its rotational energy. But it's not a fair trade, we get the better deal. Normally, if you fire a rocket, you exchange chemical energy for kinetic energy. This is like pushing yourself forward in a swimming pool. But if you fire a rocket inside the ergosphere, it's like pushing yourself forward in a wave pool. The rotational energy of the waves gives you a much stronger boost than you could get just by pushing yourself. The boost from the rotation of the black hole is so big that you leave the ergosphere with much more energy than you entered it. The black hole gives a tiny amount of its rotational energy to you and slows down a little. Obviously, this requires a lot of food. Fortunately, black holes aren't picky eaters. An advanced future civilization would probably harvest asteroids to drop them into the black hole when they needed an energy boost. But there's an even better way to get energy from a black hole, and oddly enough, it builds the biggest bomb any living thing could ever hope to build. The black hole bomb. We only need 2 things to build a black hole bomb: a fast-spinning black hole and a big mirror. The mirror has to completely envelop the black hole, which is similar to a Dyson sphere, a megastructure that harvests the energy of an entire star. Although our mirror would be easier to build, mirrors are simpler and black holes are much more compact than stars. If we made the mirror 10 centimeters thick, the metal of a big asteroid would probably be enough material for a black hole with the mass of our Sun. Once our mirror is in place, we only need to open a window and shoot electromagnetic waves at the black hole. You can imagine what happens next by imagining tossing a ball at a wall and it coming back faster than a bullet. The waves hit the black hole at light speed. A small proportion of the waves falls past the event horizon to disappear forever. But a much larger amount sloshes through the ergosphere, where the black hole forces some of its rotational energy on them and amplifies them. They now begin super radiant scattering, which are fancy science words meaning bouncing around between mirror and black hole and getting stronger. Every time they go around, they are getting exponentially stronger. By opening some windows in the mirror, we can extract the energy from the waves as fast as they grow, which we could use, in theory, to create what would be, for all practical purposes, an endless source of energy for trillions of years. Or we could blow it up. If the waves are not released, they will continue to get stronger and stronger and take more and more energy from the black hole until the mirror shatters. A supermassive black hole would release as much energy as a supernova, making the bomb the largest explosion any living being could ever create. The last home in a dying universe. The beauty of the black hole bomb, the Penrose process, and the super radiant scattering is that they are not science fiction. In the far, far future, this might be the only way to survive in our dying universe. After all the red dwarfs have cooled down and all the white dwarfs transformed into black dwarfs, the universe will turn dark forever. Rotating black holes might be the only sources of energy in the entire universe that life could harvest. If so, the last living being in existence might one day end its life around a black hole, which is equally chilling and uplifting. It turns out that even without any light, there are places we can go. Mars is a disappointing hellhole lacking practically everything we need to stay alive. It looks like we'll only ever have small crews spend a miserable time hidden underground. Except we could terraform it into a green new world. But to solve the planet's problems, we first need to make it worse and turn it into oceans of lava with gigantic lasers. This isn't a far-fetched science fiction tale. Terraforming Mars is possible on the kind of timescale our ancestors built great monuments in. If humanity solves some of its pressing problems and ventures into space to expand into the solar system, this may not be that far off. Okay, so how do we terraform Mars quickly? Well, it's complicated. Mars is dry and has no soil to grow anything. Its atmosphere is too thin to breathe or protect us from radiation, giving you a high risk of cancer. So to turn it into a new home for humanity, we have to give it a proper atmosphere similar to Earth's. It should be made of 21% oxygen, 79% nitrogen, and a tiny bit of CO2 at an average temperature of 14 degrees Celsius and under 1 bar of pressure. We have to create oceans and rivers, and then the ground has to be weathered into fertile soil to host living things. Then we need to install a biosphere on the surface and prevent it all from being undone by installing protective measures that can stand the test of time. It is difficult, but a big laser makes it a lot easier. Challenge 1. The atmosphere. Some 4 billion years ago, Mars had a nice oxygen-rich atmosphere and was home to vast oceans and rivers. It held onto it for several 100 million years before it got blown away. Ultraviolet rays broke down the atmospheric gases and then the oceans until they were swept away by solar wind. Today, Mars is a dry, barren wasteland. Luckily, a sizable portion of the water is frozen in deep reservoirs and in the polar ice caps, enough to create a very shallow ocean. And enormous amounts of oxygen are bound as minerals in the Martian rocks, like the oxygen in the iron oxides that give the planet its rust-red color, as well as carbon dioxide in carbonates. To free these gases, we need to reverse the reactions that lock them away by using thermolysis, which occurs at temperatures as high as on the surface of the Sun. In short, we want to melt the surface of Mars. The best way to do that would be to put lasers in orbit, aiming their beams down on Mars. The most powerful laser today is the Eli NP, able to produce beams of 10 petawatts of power for a trillionth of a second. To melt Mars, we need a laser twice as powerful that runs continuously. The easiest way is to use a solar-pumped laser that can be powered directly with sunlight. At its core are metal-infused glass rods that absorb energy and release it as a laser beam. If we build an array of mirrors in space about 11 times the size of the United States, we can focus enough sunlight onto them to melt Mars. Let's do it! As the lasers hit the surface, about 750 kilograms of oxygen and some carbon dioxide emerge from every cubic meter of rock melted. If we are efficient, our lasers only need to melt through the top 8 meters of the surface to get enough oxygen. It would look terrifying. The skies would be shrouded in storms, while the ground would glow red-hot, crisscrossed by currents of lava. Tireless laser beams sweep over the landscape, leaving trails too bright to look at. After they pass, the ground cools quickly. A strange snow falls, the ashes from all the elements that solidify as they cool down, like silicon and iron. Mars is still a cold planet at this point. A happy side effect of this inferno is that all the water in the polar ice caps and even deep underground rises into the sky as hot steam, forming clouds that rain down over the entire planet. They would wash out the nastier gases from the atmosphere like chlorine and carry away harmful elements that accumulated on the surface. In the end, they would form shallow oceans, saltier than on Earth. We might need to do an extra cleanup afterwards. It would take about 50 years of continuous lasering to create our oxygen atmosphere. We could use this opportunity to dig deeper in some places to create the basins for salty oceans or rivers and spare some landmark features like Olympus Mons and Valles Marineris. We're not done though. The resulting atmosphere is nearly 100% oxygen and only 0.2 bar. It's hard to breathe and very flammable. To make it similar to Earth and a lot safer, we need to add a lot of nitrogen, which Mars is sadly lacking. we have to import it. The ideal source is Titan, a large moon of Saturn, covered in a thick atmosphere that's almost entirely nitrogen. We just have to move 3,000 trillion tons from the outer solar system to Mars. While that's not easy, it is doable. To process that much of Titan's atmosphere, we have to construct giant automated factories on its surface powered by our lasers to suck in the atmosphere and compress it into a liquid. This gets pumped into bullet-shaped tanks, which a mass driver shoots all the way to the red planet, where they explode and mix with the oxygen. We've already been able to send individual missions to Saturn in just a few years. With enough resources, it should be possible to complete the task within 2 generations. Of course, it would be much more convenient to have nitrogen left over from terraforming Venus on the side. We explained this in detail in another video. So, about a century after the start of the terraforming process, we have a breathable atmosphere that has the right gases. If the liberated CO2 isn't enough to warm it up to temperatures we can stand, we just add some super greenhouse gases. Mars at this point resembles a black marble from all the cooling lava, spotted with growing oceans and red patches where the old surface remains untouched. It's still a wasteland, no better than a desert on Earth. We need to fill it with life. Challenge 2. Biosphere. Installing a biosphere on a new planet is very difficult. Unexpected interactions between species or sudden diseases can destabilize it to the point of collapse. We would probably begin by seeding our young oceans with phytoplankton. Without competition, it would bloom rapidly, filling up the oceans to become the bottom of an aquatic food chain. They can be followed by tiny zooplankton, then by fish, maybe even sharks and whales. If things go well, life in the oceans will thrive. Life on land is harder. Plants need nutrient-filled ground to sink their roots into, but most of the surface is the congealed remains of lava and ash. We could wait for thousands of years for water and wind to grind it down into finer sands, or try to do it manually. But we want to be quick, and we have a big laser. Turning the beam on and off in rapid succession would cause the ground to quickly heat up and contract, which breaks it into smaller and smaller pieces. Add a bit of water and you get a sort of dark mud. Into this mud, we can mix fungi and nitrogen-fixing bacteria. They're able to absorb nitrogen and convert it into nitrate compounds to feed plants. The first plants we want to bring are native to volcanic islands on Earth, since they're perfectly suited to the laser-blasted Martian landscape. Eventually, the enriched mud becomes the foundation for grasslands and forests. In Mars's lower gravity, trees can become very tall very fast. Their roots gather the nutrients they need and then dig deeper to turn more rocks into soil, forming a self-sustaining ecosystem. At this point, we can slowly introduce more plant varieties, insects and animals. Not mosquitoes though. The new biosphere needs to be maintained to prevent it from falling out of balance. If plants grow too quickly and absorb too much carbon dioxide, the planet cools down too much. If key species die out, we could see populations collapse faster than they could recover. On Earth, other species would move in to fill the void, but our Martian biosphere is not as flexible. It takes hundreds, if not thousands of years before Mars becomes a stable environment. But eventually, the planet will have the potential to sustain large human colonies. With air, water and food available, we can finally call Mars, black, blue and green, our home. A giant volcanic island in space. Will it last though? Challenge 3. The long-term future. There is a problem we haven't addressed. Mars's core does not produce a magnetic field, so it doesn't have enough protection from solar radiation or cosmic rays. This becomes dangerous for the long-term health of Martian populations. So, as a final step, we need an artificial magnetic field. It doesn't have to be huge like Earth's, it just needs to deflect the solar wind enough so that it doesn't touch Mars. The easiest way is to construct a magnetic umbrella far ahead of Mars that splashes the solar wind to the sides. A big superconducting ring powered by nuclear facilities is all it takes. It would orbit at the Mars-Sun L1 point, keeping it constantly in between the Sun and Mars and protect the new atmosphere. And that's it. Terraforming Mars would take some work, hefty resources, and probably a century or 10, but it would be the first time we've lived in a home designed and shaped solely by us and for us. A first step towards our future among the stars. Welcome to the Kurzgesagt lab. Let's conduct a few stellar experiments. We'll first add some more mass to this protostar. More. A bit more. Wow, we've just created a blue giant, a star with 10 times the mass of our Sun. Let's now add a couple of million years and see what happens. A supernova. Breathtaking. And look, it leaves behind a black hole. Fascinating stuff. Now we record our findings. Be careful to preserve the sparkle. It's now time for Duck's final inspection. This one is always a nail-biter. He has incredibly high standards. Luckily for us, our work is scientifically accurate, offers an overview of important astrophysical processes, and is a real stunner. Duck approves. Looks like it's ready to be shared with the world as a poster, a very special piece of Kurzgesagt you can take home and touch. You can get this very special poster along with many other sciencey and spacey things created with love and care from our shop. Here in the Kurzgesagt labs, we test very important ideas to see what happens when you blow things up or play with black holes. Many of you suggested that we look into an idea that sounds reasonable: shooting nuclear waste into space. It's one of those concepts that seems like an easy fix for one of the main problems with nuclear energy. But it turns out this idea is not just bad, but horribly bad, and it gets worse the longer you think about it. Why is that? What is nuclear waste? Nuclear waste is a fuzzy term and comes in categories which vary from country to country. But in general, there are 3 broad levels. 90% is low-level nuclear waste, tools, gloves, or trash used at a nuclear facility that could be weakly contaminated with some short-lived radioactivity. This stuff is generally safe for normal disposal. 7% is intermediate-level nuclear waste, mostly materials that have been in close proximity to a reactor core long enough to become dangerously radioactive. With proper handling, it's either safely buried or melted down and mixed into glass or concrete and stored deep underground. So 97% of nuclear waste is similar to toxic byproducts from other industries. Not great, not terrible. We can handle it. The remaining 3% is where our problems begin. High-level nuclear waste is very concentrated spent fuel taken out of a reactor core. Formerly uranium, it's now made of various dangerous and often highly radioactive elements. As a bonus, it's also incredibly hot and not easy to handle at all. This is what we want to shoot into space. All in all, around 440 active nuclear reactors create about 11,000 tons of high-level nuclear waste each year. Since 1954, we've accumulated 400,000 tons of dangerous radioactive waste. Most countries are dealing with it by not dealing with it and kicking the can towards the future. Great, so let's launch it into space. According to scientists, space is big, and nobody lives there, so it seems perfect for yeeting away this mess. There are a few tiny problems though. Problem 1, stuff ain't cheap. Even though spaceflight is getting more affordable, it's still extremely expensive. Just to get something into low Earth orbit costs on average about $4,000 per kilogram. Putting that into perspective, it costs about $1,600 to mine, separate and fabricate 1 kilogram of nuclear fuel, so launching waste into space has suddenly made nuclear fuel for reactors way more expensive and greatly increased the cost of the electricity they produce. To launch 1 reactor's worth of nuclear waste would cost at least $100 million per year. To deal with all the 440 operational nuclear power plants' high-level nuclear waste would cost some $44 billion per year for space launch before packaging, transport and security costs are added. Okay, let's pretend we don't care. Currently, we couldn't shoot all the nuclear waste into space even if we wanted to. There just aren't enough rockets. In 2021, we saw a record 135 launches into space. If we repurposed each of those rockets and filled them all with nuclear waste, the total amount that could be lifted into a low Earth orbit, which is the closest orbit above the atmosphere, is nearly 800 tons. We'd need at least 14 times more rockets to handle just today's nuclear waste, let alone get rid of the hundreds of thousands of tons in temporary storage. We would need to create entire new space industries to keep up with the demand for giant, toxic space trash trucks. And it gets worse. Problem 2. Space is hard. We only made the calculation for low Earth orbit, where we send most of our rockets and satellites. Littering the space around Earth with thousands of casks of spent nuclear fuel would be a nightmare for space junk management and satellite collision avoidance. Worse still, at this altitude, there's still a little bit of atmosphere causing a tiny bit of drag, so we might have nuclear waste raining down from space within just a few years. Experts would call this a huge problem. Clearly, we have to launch our waste further. If we wanted to send it to, perhaps, the Moon, we either need way more rockets or we need to build much bigger ones, making it even more expensive. A single Saturn V, the rocket used by the Apollo program, which cost around $1.5 billion adjusted for inflation per launch, could get about 43.5 tons from the Earth to the Moon. So we'd need about 260 Saturn V rocket launches every year. And of course, using the Moon as target practice for nuclear waste-tipped rockets kind of makes a huge mess. So maybe don't aim for anything. Space is empty. Do we really need a target? Shooting waste in any random direction is, you guessed it, also a bad idea. Orbits are loops, which means they have a tendency to come back to where they started. Put enough in the sky in random directions, and you'll get one back eventually. So we'd want to launch our nuclear waste deep into space, which means we need even bigger rockets that would be even more expensive. Not that we would be completely safe then. Earth might run into these interplanetary caskets at some time in the far future and experience a pretty meteor shower made from radioactive dust. Okay, how about we shoot it into the Sun? Ironically, the Sun is pretty hard to hit. While the Sun has very strong gravity, everything on Earth is moving with respect to the Sun, including the rockets that we launch, meaning a rocket would have to cancel out all the orbital motion it has around the Sun so it can stop orbiting and fall in. Because of this, it's actually easier to launch a rocket entirely out of the solar system than it is to launch it into the Sun. But to do either of these things, we need even bigger rockets, probably the biggest we've ever built. Nothing works. The thing is, it gets even worse. Problem 3. Rockets go brrrr. Rocket engineering has taken huge steps since the Apollo era. We've made them relatively safe. We've mostly replaced the toxic explosive cancer fuels of the past decades with much saner mixes of liquid oxygen and hydrogen or kerosene. The newest designs even land themselves so that they can be reused. And yet, out of the 146 launches in 2021, there were 11 failures, which means that a sizable number of our rockets carrying high-level radioactive waste would be exploding on the launch pad, or in the worst case, disassembling at high altitude or crashing from hypersonic speeds. Each failure would be at least equivalent to a mini Chernobyl, but instead of being contained under a slab of concrete, spread throughout the atmosphere. Radioactive particles could make their way to faraway places by riding on the winds. Most would fall into the ocean, but some would land on the inhabited parts of the world. They could cover farmlands and get concentrated into our food or enter our water supply, which is, well, bad. Imagine regular large-scale nuclear disasters happening. People wouldn't be happy. Conclusion and opinion part. Nuclear waste is scary, but the fear of it and horrible ideas like shooting it into space reveals how bad we are at understanding risk, because the largest amounts of radioactive elements like uranium and radon are actually released by coal. Burning millions of tons of coal each year leaves ash as a waste product that includes about 36,000 tons of radioactive materials. Less radioactive than high-level nuclear waste, but there's also a lot more of it, and it's handled way less carefully. Some of this ash is caught by filters, but most is simply pushed back into leaky mines, shoved into piles exposed to the wind, or poured into ponds that regularly spill into rivers and lakes. Living within 1.6 kilometers of an ash pile increases your cancer risk up to 2,000 times over the acceptable limit. And this is on top of other toxic chemicals like heavy metals and, of course, their massive CO2 emissions. And yet, while nuclear energy is flawed and its current form may only be a transitory technology, nuclear power plants are a harder sell than coal. Nuclear waste and the lack of willingness to deal with it are a real issue. It's not insurmountable though. There are good methods to handle it, like burying it deep underground or reprocessing some of it into new fuel. But however we ultimately deal with this issue, we hope one thing is clear: shooting nuclear waste into space is one of the worst ideas ever. What would happen to you if a black hole the size of a coin suddenly appeared near you? Short answer, you'd die. Long answer, it depends. Is it a black hole with the mass of a coin, or is it as wide as a coin? Suppose a US nickel with a mass of about 5 grams magically collapsed into a black hole. This black hole would have a radius of 10 to the power of minus 30 meters. By comparison, a hydrogen atom is about 10 to the power of minus 11 meters. So the black hole compared to an atom is as small as an atom compared to the sun. Unimaginably small. And a small black hole would also have an unimaginably short lifetime to decay by Hawking radiation. It would radiate away what little mass it has in 10 to the power of minus 23 seconds. Its 5 grams of mass will be converted to 450 terajoules of energy, which will lead to an explosion roughly 3 times bigger than the atomic bombs dropped on Hiroshima and Nagasaki combined. In this case, you die. You also lose the coin. If the black hole had the diameter of a common coin, then it would be considerably more massive. In fact, a black hole with the diameter of a nickel would be slightly more massive than the Earth. It would have a surface gravity a billion times greater than our planet currently does. Its tidal forces on you would be so strong that they'd rip your individual cells apart. The black hole would consume you before you even realized what's happening. Although the laws of gravity are still the same, the phenomenon of gravity that you'd experience would be very different around such dense objects. The range of the gravitational attraction extends over the entire observable universe, with gravity getting weaker the farther away you are from something. On Earth right now, your head and your toes are approximately the same distance from the center of our planet. But if you stood on a nickel-sized black hole, your feet would be hundreds of times closer to the center, and the gravitational force would be tens of thousands of times as large as the force on your head and rip you into a billion pieces. But the black hole wouldn't stop with just you. The black hole is now a dominant gravitational piece of the Earth-Moon black hole of death system. You might think that the black hole would sink towards the center of the planet and consume it from the inside out. In fact, the Earth also moves up onto the black hole and begins to bob around as if it were orbiting the black hole, all while having swathes of mass eaten with each pass, which is much more creepy. As the Earth is eaten up from the inside, it collapses into a scattered disk of hot rock surrounding the black hole in a tight orbit. The black hole slowly doubles its mass by the time it's done feeding. The Moon's orbit is now highly elliptical. The effects on the solar system are awesome. In the biblical sense of awesome, which means terrifying. Tidal forces from the black hole would probably disrupt the near-Earth asteroids, maybe even parts of the asteroid belt, sending rocks careening through the solar system. Bombardment and impacts may become commonplace for the next few million years. The planets are slightly perturbed, but stay approximately in the same orbit. The black hole we used to call Earth will now continue on orbiting the Sun in the Earth's place. In this case, you also die. Leaving Earth to find new homes in space is an old dream of humanity and will sooner or later be necessary for our survival. The planet that gets the most attention is Mars, a small, toxic and energy-poor planet that just about seems good enough for a colony of depressed humans huddled in underground cities. But what if we think bigger? What if we take Venus, one of the most hostile and deadly places in the solar system, and turn it into a colony? Not by building lofty cloud cities, but by creating a proper second Earth. It might be easier than you think. Venus is by far the hottest planet in the solar system, with a surface temperature of 460 degrees Celsius, hot enough to melt lead. This heat is due to the most extreme greenhouse effect in the solar system. CO2 is great at trapping heat. Even a rise from 0.03% to 0.04% in Earth's atmosphere is heating up our planet right now. Venus's atmosphere is 97% CO2. Also, Venus's atmosphere is 93 times denser than Earth's. Standing on Venus's surface would feel like taking a dive about 900 meters deep into the ocean. The pressure would kill you instantly. It's a truly horrible place, so why should we even bother? First and foremost, Venus is almost as big as Earth and has 90% of its surface gravity. Surface gravity is a big problem when colonizing the solar system because it's very likely that long stays in low-gravity places will have negative health effects. Venus's size means it could be the second largest habitat in the solar system, a new home for billions of humans and trillions of animals, with oceans, lush forests, and a beautiful blue sky. A properly terraformed Venus may be the most pleasant place to live outside of Earth. While we can't exactly terraform Venus today, a slightly more ambitious future version of us could take this project on. It will take a few generations to complete and be a huge challenge like building the Great Pyramids was for our ancestors. But then, it's not like humans have never started projects that took more than a lifetime to complete. Okay, let's do it. Before anything else, we need to cool Venus down and remove the gas that makes up the extremely heavy atmosphere. As mentioned, there's a lot of it, around 465 billion tons. How do we do that? There are a few options. We could create giant solar collectors powering a huge array of laser beams that heat up the atmosphere so much that it's blasted into space. Although we would need thousands of times the entire power generating capacity of humanity, and it would still take thousands of years to remove the atmosphere. Another way is to sequester the atmosphere, binding the CO2 in different compounds through chemical reactions. We could mine elements like calcium or magnesium on Mercury and shoot them at Venus via mass driver systems, electric rails that make rockets unnecessary on smaller planets. The metals would combine to bind the CO2 into different carbonates basically forever. But the scale makes the whole thing impractical. We would need several 100 billion tons of material to sequester the CO2 this way. Seems like a waste of material and might take too long. An equally ridiculous idea that could actually work is to put Venus in the shade, literally, by constructing a huge mirror to blot out the sun to just freeze the atmosphere. The mirror doesn't need to be complex or massive, just a very thin foil with a little structural support. Building such a large flat surface so close to the sun will turn it effectively into a solar sail and push it out of position. So instead of one giant circular object, our mirror will consist of many different pieces. Annular slats of angled mirrors can reflect sunlight from one set of mirrors to the next. Mirrors would be angled, reflecting light from one to another until the light is redirected to the back, balancing the force on the front and holding them in position. After a few years of getting the infrastructure in place, things start slowly and then escalate. For the first few decades, the atmosphere slowly cools down but stays dense and deadly, until after some 60 years, it reaches the critical temperature of 31 degrees Celsius. Suddenly, the Great Flood begins on Venus as CO2 turns to liquid at this pressure and begins to rain down. A constant global rainstorm of unbelievable proportions lasting 30 years. The pressure and temperature suddenly begin to drop in unison. For almost a century, puddles turn into lakes and oceans. The surface temperature is now minus 56 degrees Celsius and the pressure has dropped to only 7 times the pressure on Earth. Finally, at a really unpleasant minus 81 degrees Celsius, the CO2 oceans begin to freeze and the rain turns into snow. This leaves us with a frozen Venus covered in oceans as hard as rock and gigantic CO2 glaciers. What remains of the atmosphere is mostly nitrogen at about 3 times Earth's surface pressure. If you don't mind freezing and suffocating, you can now take a stroll over Venus's surface. But the frozen CO2 remains a bit of a problem. At some point, we want to warm up the planet, but if we do, the CO2 ice will melt and fill up the atmosphere again. So we need some way to keep it from doing that. One is to simply cover it all with cheap plastic insulation and cover it up with ground-up Venus rock or water oceans. Although some planetary scientists will be very stressed out about us building a new planet containing a potential time bomb like that. A few unfortunately timed volcanoes could melt a lot of CO2 at once and ruin everything. Another obvious solution is to shoot it all out into space and collect it into a small moon for storage and future use. We can make this more efficient by using mass drivers instead of rockets, but moving all that mass will still be a pretty intense challenge that will take some time to solve. Whatever we end up doing with the atmosphere, to move forward we need water, which we could get from ice moons. Europa, a moon of Jupiter, has twice as much water as Earth's oceans. Now, catching a moon and transporting it through the solar system is not exactly easy. So instead, it might be easier to cut chunks of ice off Europa with an army of construction drones and shoot them at Venus using more of those mass drivers. Space tethers could save us a lot of effort and energy here. We made a whole video explaining how they work, but in a nutshell, they are slings that can take a payload on both ends. On Europa, they do most of the work needed to catapult our ice to Venus. The ice hits the Venus tethers, which gently drop it into the atmosphere, where it falls down as snow. In exchange, the Venus tethers get to catch CO2 ice shot up from below and accelerate it into orbit. We can remove excess nitrogen using this same method to further lower our atmospheric pressure. After a few decades or centuries, Venus would be covered by a nice, shallow, frozen ocean a few hundred meters deep. It would look extremely different from today. A few continents and countless islands have formed. This is beginning to look a bit like our planet. Now the last and most magnificent phase of terraforming begins, making the atmosphere breathable and adding life. First, we need light though, and we need to heat the planet up again. A Venus day is 2,802 hours long, more than 116 Earth days. So if we just remove our giant mirror, we would grill half of our planet. Even without the massive atmosphere, temperatures would reach unbearable levels. The simplest way to create a day-night cycle and let some energy in again is with another set of mirrors to illuminate our continents and melt our water oceans, which would let us completely control how much energy we get and where it goes. The atmosphere is now mostly made up of nitrogen and basically devoid of oxygen. So the first inhabitants will likely be trillions and trillions of cyanobacteria, which can get photosynthesizing and release oxygen. We know that they can quickly turn around the atmosphere of a planet because billions of years ago they were probably responsible for turning the toxic atmosphere of our young Earth into an atmosphere with enough oxygen for more complex animal life. But not only that, cyanobacteria can fix nitrogen from the atmosphere and turn it into nutrients that can be used by living beings. This way, they will essentially fertilize our dead ocean water and prepare it for more complex organisms. On land, our colonists need to grind down some of the former Venusian surface to make soil for nitrogen-fixing plants to grow on. Eventually, billions of trees would spread, creating large forests covering massive parts of the continents. Venus would turn green. To speed things up, CO2 would be strategically released to supply the plants and cyanobacteria. Areas already covered with plants could get extra daylight from our orbital mirrors, so the plants would be active for most of each day. Maybe we won't have to do this with the same plants and animals we know today. As genetic engineering matures and our understanding of genetics and the machinery of life expands, we might just engineer life as we need it. All in all, it would take several thousand years to make the atmosphere breathable by humans. In the meantime, you could stroll around with nothing more than regular clothes and an oxygen mask. Settlers would enjoy a vast new planet filled with resources and bathed in sunlight. They might think of new ways to use the vast amounts of carbon dioxide ice and nitrogen orbiting in space above. Industrial processes, rocket fuel, or even boosting the terraforming of another planet like tiny Mars. Venus is fully terraformed. Animals roam through vast ecosystems. Cities are being constructed. Billions of settlers and their descendants make this world their home. They will see images of the past, how Venus was once the most hostile planet around, how it took hundreds of years to freeze hell and to ship in the oceans, and another few thousand years to make it possible to breathe freely. They will barely be able to believe it. Okay, maybe it's not that easy to terraform Venus, and a lot of things must go right for this future to become reality. But it is possible, and with technology that is within the reach of a motivated and slightly more advanced humanity that wants to venture into space. The only thing that's stopping it is our imagination, and that at least is a problem that's easy to overcome. Matter as we know it. Atoms, stars and galaxies, planets and trees, rocks and us. This matter accounts for less than 5% of the known universe. About 25% is dark matter and 70% dark energy. both of which are invisible. This is kind of strange because it suggests that everything we experience is really only a tiny fraction of reality. But it gets worse. We really have no clue what dark matter and energy are or how they work. We are pretty sure they exist though. So, what do we know? Dark matter is the stuff that makes it possible for galaxies to exist. When we calculated why the universe is structured the way it is, it quickly became clear that there's just not enough normal matter. The gravity of the visible matter is not strong enough to form galaxies and complex structures. Stars would more likely be scattered all over the place and not form galaxies. So we know there is something else inside and around them. Something that doesn't emit or reflect light. Something dark. But besides being able to calculate the existence of dark matter, we can see it, kind of. Places with a high concentration of dark matter bend light passing nearby, so we know there's something there that interacts with gravity. Right now, we have more ideas about what dark energy is not than what it is. We know dark matter is not just clouds of normal matter without stars because it would emit particles we could detect. Dark matter is not antimatter because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, very compact objects that violently affect their surroundings, while dark matter seems to be scattered all over the place. Basically, we only know three things for sure. 1. Something is out there. 2. It interacts with gravity. 3. There is a lot of it. Dark matter is probably made up of a complicated exotic particle that doesn't interact with light and matter in a way we expect, but right now, we just don't know. Dark energy is even more strange and mysterious. We can't detect it, we can't measure it, and we can't taste it, but we do see its effects very clearly. In 1929, Edwin Hubble examined how the wavelength of light emitted by distant galaxies shifts towards the red end of the electromagnetic spectrum as it travels through space. He found that fainter, more distant galaxies showed a large degree of redshift. Closer galaxies, not so much. Hubble determined that this was because the universe itself is expanding. The redshift occurs because the wavelengths of light are stretched as the universe expands. More recent discoveries have shown that the expansion of the universe is accelerating. Before that, it was thought that the pull of gravity would cause the expansion to either slow down or even retract and collapse in on itself at some point. Space doesn't change its properties as it expands. There's just more of it. New space is constantly created everywhere. Galaxies are tight-bound clusters of stuff held together by gravity, so we don't experience this expansion in our daily lives, but we see it everywhere around us. Wherever there is empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else we know and that keeps getting stronger as time passes by. Empty space has more energy than everything else in the universe combined. We have multiple ideas about what dark energy might be. One idea is that dark energy is not a thing, but just a property of space. Empty space is not nothing, it has its own energy. It can generate more space and is quite active. So as the universe expands, it could be that just more and more space appears to fill the gaps, and this leads to a faster expanding universe. This idea is close to an idea that Einstein had back in 1917 of a concept of a cosmological constant, a force that counteracted the force of gravity. The only problem is that when we tried to calculate the amount of this energy, the result was so wrong and weird that it only added to the confusion. Another idea is that empty space is actually full of temporary, virtual particles that spontaneously and continually form from nothing and then disappear into nothing again. The energy from those particles could be dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field which permeates the entire universe, but somehow has the opposite effect on the universe than normal energy and matter. But if it exists, we don't know how and where, or how we could detect it. So there are still a lot of questions to answer. Our theories about dark matter and dark energy are still just that, theories. On the one hand, this is kind of frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we feel we're on top of things, we're still very much apes with smartphones, on a tiny fragile island in space, looking into the sky, wondering how our universe works. There is so much left to learn, and that is awesome. Black holes are the most powerful and extreme things in the universe, and they're wildly weird and complicated. What would happen if you fell inside one, and what are they really? First, we need to talk about space and time. Space and time are the grand stage where the play of the universe unfolds. But space isn't a fixed stage, and time doesn't tick the same for everyone everywhere. In short, they're relative. Matter bends space, and bent space tells matter how to move. Put some stars and planets on the stage, and it sags underneath them. That misshapen stage, with all its little warps and dips, gives us gravity. Black holes do not just bend the stage, they're like trapdoors, places with so much mass that the universe formed a no-go zone where the rules change. Most black holes form when very massive stars die. We explained this process in detail in our neutron star video. All you need to know now is that in the final moments of really massive stars, their insides implode at nearly a quarter of the speed of light. This packs so much mass so close together, creating something so dense that it sort of breaks the stage of the universe. A black hole with 10 times the mass of the Sun would be barely 60 kilometers across. If you look directly at a black hole, it looks like nothing. The space under their control is blocked by an invisible, one-way border called the event horizon. The event horizon forms a shell around a region of space that, once entered, is shielded from the rest of the universe forever. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. We can still observe black holes because of their effect on matter. Things can orbit black holes just as they can orbit the Sun or a planet. Many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot, as close orbits can speed this matter up to half the speed of light, and tiny amounts of friction and collisions between particles heat them to 1 billion degrees, making the space around these black holes, ironically, incredibly bright. What would happen if you were to try to get close or even inside a black hole? First of all, you'd see the strangest funhouse mirror in the universe. Matter isn't the only thing orbiting a black hole. Gravity is so strong near them that light can orbit too. If you hovered just outside the event horizon, at the photon sphere, in any direction, you just see yourself. Straight ahead would be the back of your own head, as light from your back travels around the black hole to your eyes. Gravity also alters the passage of time itself. The stronger the gravity, the slower time passes. While you watch the universe above you speed up, those far away will watch you in slow motion. If you chose to fly away from the black hole, you might find that eons have passed for the rest of the universe, a freakish one-way time travel trip to the future where your loved ones are long dead. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. Because your feet are closer to the black hole than your head, they feel a stronger pull of gravity, enough to pull you apart. As you descend, it gets worse. The pulling gets stronger, your body squeezed thinner and straighter, until you've been reduced to a thin stream of hot plasma, gobbled up in one final slurp, never to be seen again. Spaghettification is only a risk with smaller black holes, since they have much smaller radii. If you go to the center of a galaxy and find a supermassive black hole, you might be able to experience crossing the event horizon. As you approach the event horizon, a distant observer would think they never saw you enter it, seeing you stop and fade. The last light you emit, trickling up and out, away from the event horizon. Meanwhile, from your perspective, the void of the black hole rises up to meet you as light from fewer directions can reach you. The blackness envelops you until your only view of the universe you left is a tiny spot of light. Here, inside the event horizon, space and time are so horribly broken that real time travel is possible, so it's probably a good thing that nothing gets out. If anything could escape, it could create all sorts of time travel paradoxes and issues that break the universe. As scary as the event horizon is, it keeps us safe from that drama. Whether you have survived this long doesn't really matter, as now there's only the certainty of crushing death in your near future. Inside the event horizon, space-time itself is so bent and warped that whatever direction you move here, every forward you go leads only towards the center of the black hole. Trying to go in any direction only brings you to the center faster. To survive the longest, you must do nothing. In the center of the black hole, we find the singularity, a single point with all the matter that has ever crossed the event horizon, all crushed to a point infinitely small. There is no memory of the things that made it, as stuff disappears down the black hole trapdoor forever. The singularity makes all things equal. This actually breaks the universe in really cool ways. We've made a video about this problem if you want to learn more. But in a nutshell, everything that comes too close becomes black hole matter concentrated at the singularity. This lack of a memory of its past means that a black hole has only three properties: its mass, spin, and electric charge. Everything else is lost. They're a lot like fundamental particles in that respect. This actually means that every single black hole in the universe is the same. Sure, their mass is different and some spin faster than others, but if we were to put all the singularities into a magical physics museum, they'd be identical, like electrons. But just like fundamental particles, the properties of singularities are the best ways we can describe them on paper, rather than an accurate representation of reality. Our current theories about the universe, namely general relativity, are just not able to describe or explain them. The curvature of space becomes infinite, density becomes infinite, and our rules just don't make sense. The singularity has no surface or size, something like a divide by zero error in the universe. So singularities might not even exist, or be completely different things. But this is all we know right now from the best prediction we have from our best current theory of space-time. Also, basically everything you've ever heard about black holes, even in this video, is about theoretical black holes that aren't spinning because their maths is so much easier. But since black holes were born from dying stars that were spinning extremely quickly in their final moments, as far as we know, all black holes in the universe should be spinning right now. At incredible speeds too, up to 90% of the speed of light. This means that in reality, black holes are even more screwed up than they usually get credit for. The singularities of rotating black holes are even wilder. The rotation causes them to swell outwards into a sort of ringularity. This rotation is so powerful that space itself is dragged along. This creates another region around spinning black holes called the ergosphere, where it's impossible to stay still no matter how hard you try. Like a rushing whirlpool of space-time, the tide is irresistible, and the black hole makes you orbit it whether you want to or not. Okay, so what will happen to black holes as the universe ages and dies around them? Again, we don't know, but we have some ideas based on our current understanding of physics. Hawking radiation. In quantum field theory, the vacuum of space is boiling with quantum fluctuations. These fluctuations are creating matter and antimatter pairs of particles from nothing which only exist for a very short time before annihilating. When this happens near the event horizon of a black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation. Ultimately, the mass of this particle must come from the black hole, so over eons, black holes will shrink and radiate away. Hawking radiation is not the stuff that fell into the black hole, it's new stuff, stealing mass from it. As the black hole shrinks, the Hawking radiation gets stronger, faster and faster, until what's left eventually evaporates in a flash of high-energy radiation like a nuclear bomb. And then, nothing. But that won't happen for a long time. A black hole with the mass of our Sun has a lifetime of 10 to the power of 67 years, which means that it would take 10,000 billion years to lose 0.00000001% of its mass. But most black holes are way more massive than our Sun. The most massive supermassive black holes in the centers of galaxies have lifetimes of 10 to the power of 100 years. How long is that? Imagine an hourglass filled with 1 grain of sand for every single particle in the universe. Every 10 billion years, 1 single grain of sand falls to the bottom. If we waited for all the sand to fall down, not even 1% of the lifetimes of these black holes would have passed. There is no good concept to help our brains grasp these timescales. Will we ever truly understand black holes? Really know what's going on inside them? No one knows. We can only see their outsides, and the theories we have probably get their insides wrong. But it's okay to not know everything. It just means there's still work to be done. It means there are still mysteries to solve and big ideas to think about, which is why humans do science. In the end, we can at least be sure that we still have plenty of time left to think about them before the last one melts away. What would happen if we were to detonate a very, very powerful nuclear weapon on the Moon? Would the explosion knock its orbit towards Earth, causing tidal waves and misery? Could the Moon be destroyed, showering the Earth in a rain of meteoric death? During the Cold War, the Moon was a major target for space exploration and, military bases. So, the US Air Force commissioned a serious study into the effects of a nuclear detonation on the surface of the Moon. But just quoting stuff is boring, so let's conduct a very important scientific experiment with an imaginary 100 megaton thermonuclear warhead about twice as powerful as the most powerful bomb ever detonated. We'll also place a number of curious astronauts around the Moon as observers. Let's push the button and slow down time. For the first few milliseconds, nothing much happens outside our weapon. Meanwhile, inside, high explosives send a shockwave to a radioactive metal core, compressing it so much that it reaches criticality and starts a nuclear fission chain reaction. The 100 million degree plasma created in this first stage sets off the second stage with atomic nuclei fusing like they do in the core of a star. Very briefly, our weapon contains one of the hottest places in the universe. And only now, barely 10 milliseconds later, does the rest of the universe find out that anything has happened, as suddenly the bomb dissolves and a flaming star of nuclear death is born. So far, so good. But everything that happens now is very different from what we're used to on Earth because of one major difference. There's no atmosphere. As the fireball shines, it releases a flash of X-rays and thermal photons, a wave of silent heat which rushes outwards in all directions. On Earth, this heat would char and burn everything within a 50-kilometer radius at least. But on the Moon, without an atmosphere and oxygen-rich air, there's no burning at all. Also, there are no things to burn. The crunchy topsoil of the Moon is made from silicate rock and metals chewed to dust by eons of meteorite impacts mixed with tiny traces of water. When heated by the explosion, X-rays from the fireball vaporize a thin cloud of rock from the lunar surface, while the unlucky dust that's inside the fireball melts into glass. Any astronauts watching the show within about 50 kilometers can expect to be fried. And now we begin to see one of the biggest differences between explosions in space and on Earth. On Earth, the atmosphere fights back against the plasma bubble. Its expansion is violently stopped within moments by the pressure of the atmosphere. But this is not good news. As the fireball rams the atmosphere, it produces the most destructive part of a nuclear explosion on Earth, the shockwave. Compressed air around the explosion rushes out faster than the speed of sound, shattering buildings and roaring so loud it ruptures organs. But on the Moon there is no shockwave. No atmosphere means nothing to impede the expanding explosion in space. On the Moon, the fireball just grows in eerie silence as there's no atmosphere to stop it or to give it a voice. This would be an amazing thing to watch from a safe distance. Unfortunately, there's hardly any safe viewing distance for a nuclear explosion on the Moon. Without an atmosphere weakening the deadly ionizing radiation that can scramble DNA, anyone close enough to get a good look will be exposed to fatal amounts of radiation. But of course, that's not all. While all of this happens, the explosion hammers against the Moon, transferring about 1/10 of the explosion energy into seismic waves, powering an intense moonquake. The Moon is much smaller than the Earth, and our astronauts will feel an inescapable violent shaking no matter where they're standing. Comparable to an earthquake of 7 on the Richter scale, this shaking could seriously damage or even level infrastructure we might have built anywhere on the Moon. Those who hid on the far side of the Moon would have no idea it was an explosion. The quaking would feel like an asteroid the size of the Great Pyramid had struck. And it's not over yet. Where our bomb explodes, the ground splatters like water when a rock strikes a pond. As the explosion pushes against the surface, it may excavate as much as 100 million cubic meters of dust and rock, forming a crater 8 kilometers across, while bedrock is pulverized to rubble. Debris is shot into the sky in every direction. Again, without an atmosphere, there's no drag to slow any of it down. Much of the debris scattered never returns to the Moon, flying off faster than escape velocity. A flurry of micrometeorites have been cast off to explore the solar system, many of which will rain down on the Earth, though few will be larger than pebbles. Any satellite, astronaut or space station in the way, though, will have a really bad time. Micrometeorites are launched at many speeds and angles, allowing them to spread all over the surface of the Moon. Like bullets, they'll punch through our curious astronauts no matter where they stand. Finally, our explosion comes to an end. On Earth, the fireball rises like a hot air balloon, forming a sort of stalk. As it reaches up, cooler air is drawn in around it, rounding the top into a mushroom cloud. But on the Moon, well, you know by now, no atmosphere, no mushroom. The larger the plasma gets, the cooler it becomes, and the less energy it has to make interesting or terrifying things happen. Within seconds of pulling the trigger, the bubble reddens and fades from view. It would be visible from the Earth like a star flickering to life, only to fade out right away. A spark and then nothing. As the cloud of tiny debris reaches far above the surface of the Moon, it's illuminated by the sun for a few minutes, giving it an eerie beauty for anyone left to observe the spectacle. What about the Moon's orbit? It's basically unchanged. Trying to move the Moon with a nuke is like trying to move a truck by blowing on it. Nuclear explosions may be big, but space is bigger. Our mighty explosion just leaves another crater, one among millions. Still, anyone on the Moon will continue to not enjoy themselves. The material that ends up raining back to the Moon is radioactive, and without any natural processes to wash it away or bury it, the surface of the Moon will remain contaminated. Although fortunately the worst of the radiation will have decayed to a level comparable to natural levels from cosmic rays in about a year. In conclusion, we can say with confidence that while the Moon itself does not care about being nuked, and will barely notice, using the Moon as a nuclear test ground kind of ruins it for everyone trying to spend some time there or to build something useful. So maybe we should just not do that. The Sun. Smooth and round and peaceful. Except when it suddenly vomits radiation and plasma in random directions. These solar flares and coronal mass ejections, or CMEs, can hit Earth and have serious consequences for humanity. How exactly do they work? How bad could they be? And can we prepare for them? While the Sun seems pretty solid, it's actually like a very hot ocean. So hot that it rips atoms into electrons and nuclei, all flowing around each other in a plasma. This plasma is pushed around and shaped by the Sun's magnetic field, similar to how the Sun's gravitational field reaches out to the planets and shapes their orbits. But magnetism is very different from gravity. Magnetism is one part of a dual force, electromagnetism. Electricity creates magnetic fields, and magnetic fields create electricity. On the Sun, the plasma made of electrically charged protons and electrons creates a magnetic field as they move, and this magnetic field then shapes the flow of particles. They're stuck in a dynamic feedback loop called a dynamo, which keeps the Sun's magnetic field alive. This magnetic field stores enormous amounts of energy and leaks out over the solar system. It carries with it a constant trickle of solar plasma like a light rain known as the solar wind, creating a sort of space weather. But it isn't always calm and smooth. As the sun's plasma churns and flows around itself, its magnetic field gets all kinked and twisted. This creates magnetic knots that build up enormous amounts of energy. When the magnetic knots break, like a tangle of springs exploding outwards, the sun can vomit plasma and other awful things into the solar system. These solar storms come in many types, like solar flares, a tidal wave of high-energy radiation. They race through the solar system at the speed of light, sweeping up protons in the solar wind, accelerating them into a high-speed solar proton storm. Then there are coronal mass ejections, which rip millions or billions of tons of plasma from the sun's atmosphere, catapulting it through the solar system at speeds of up to 9 million kilometers per hour. When these monsters hit us, nothing happens on Earth. While even smaller storms can damage satellites, affect radio communication, or be dangerous to astronauts, for people on the surface, space weather is harmless. Earth's atmosphere protects us from the worst effects of a solar flare by absorbing the blast of X-rays high up in the atmosphere, well before it reaches the surface. The electrified plasma from a CME is deflected by the Earth's magnetic field, diverting the energy storm to the north and south poles, where energetic particles fall into the atmosphere, causing the atmosphere to glow and creating beautiful auroras. As with any sort of weather, most of the time things are fine. Sometimes there are hurricanes though, or in the case of the sun, solar superstorms. And we know that they happen once or twice every century. If one were to happen today, we would first detect strong solar flares, a sort of flash before the much more dangerous thunder. The thunder is a CME, consisting of billions of tons of hot magnetic plasma that crosses the 150 million kilometers between the sun and Earth in less than a day. When it arrives, it causes a shock wave that violently compresses the Earth's magnetic field and transfers energy into the magnetosphere. But it can get worse. If the magnetic field of the CME is aligned to Earth's in just the right way, the two magnetic fields merge. As the magnetic cloud passes over Earth, it stretches the Earth's field into a long tail. Eventually, the energy stored in the tail becomes too much to contain. It snaps and explosively releases its energy towards Earth. A geomagnetic storm has begun. A few hundred years ago, nobody would have cared. This storm gushing over the Earth is not relevant for machines made out of meat and bones. But it's very relevant for machines made out of metal and wire. Remember the dynamo? Magnetism creates electric currents. Earth in the 21st century is covered in millions of kilometers of wires transporting electricity and a complex grid of machines like transformers that make this transfer possible. A CME's energy can induce currents in our power grid that can either completely shut it down or worse, destroy the transformer stations that keep our grid running. This has happened already, like when the Quebec power grid failed after a strong solar storm in 1989. But in general, our engineers know how to deal with these storms, and so we usually don't even notice. The last time a solar hurricane washed over Earth was in 1859. The Carrington event, the largest geomagnetic storms ever observed on Earth. Massive auroras occurred as far south as the Caribbean. In some places, they were so bright that people got up thinking the sun was rising. Luckily, we only had one sort of modern technology: telegraph systems. They failed all over the world, shocking their operators and chucking out sparks. Today, we have a tad more technology, and our luck may run out soon. Another bad solar storm is bound to happen eventually. A storm as strong as the Carrington event missed Earth only by a small margin in 2012. Studies projected that it would have inflicted serious damage to electronic systems globally, costing up to $2.6 trillion to the US alone. The time to replace all the damaged systems was estimated at between 4 and 10 years. It's hard to say how bad it could have been. Experts disagreed. Some assumed there would just be temporary blackouts, but others worried it could be much worse. We won't know for sure until a big solar hurricane hits us. The probability of such an event is estimated to be 12% per decade. That's about a 50-50 chance of at least one in the next 50 years. And there is more unsettling news. A 2019 paper found that even calm stars like our Sun can create superflares every few thousand years. Eruptions orders of magnitude stronger than the strongest storms we have observed in the solar system. If such a storm hits us unprepared, the consequences could be catastrophic. It's hard to overstate how much we depend on electricity. It's not just the lights at home, it means no computers, no communication, no navigation. A sustained power outage might lead to a breakdown of the supply chain, water supply systems failing, and hospital generators running dry. Supermarkets not being refilled while food rots in the fields. The lack of power might make it extremely hard to reboot our broken power grid, taking years or decades to restart our starving civilization. Okay, time to panic. As much as daily newspapers might like for solar storms to send us back to the Stone Age, they probably won't. Fortunately, even though solar storms aren't preventable, virtually all of their nasty side effects are. Scientists observing the Sun have a few hours up to a few days to see a CME coming. And the engineers working the systems that keep the world running are well aware of the risks posed by solar storms. Transformers and substations can be taken offline. Short preventative blackouts, or in other words, by unplugging stuff. Engineers can open up extra lines to dissipate the extra power, and with investment and upgrades cheap compared to those other natural disasters require, we could protect the world's electric grid against even the nastiest of storms. But we do need to prepare. While the risk is manageable, it is real. For while our Sun bathes us in warm and pleasant light, one day it might send a monster our way that we better be ready for. Black hole stars may have been the largest stars that ever existed. They burned brighter than galaxies and were larger than any star today or that could ever exist in the future. But besides their scale, what makes them special and weird is that deep inside, they were occupied by a cosmic parasite, an endlessly hungry black hole. How is that even possible? Black hole stars take the weirdness of black holes and go beyond to break everything we know about how stars form and grow. They were only possible during a short window of time in the early universe, but if they existed, they would solve one of the largest mysteries of cosmology. Black hole stars were excessive any way you look at them. The most massive stars today may have about 300 solar masses. A black hole star had up to 10 million solar masses of nearly pure hydrogen. Let's take a moment to look at what this means visually. The Sun, Wesen, LL Pegasi, the largest star, and finally the black hole star. Its scale is beyond words. Over 800,000 times wider than our Sun, 380 times larger than the largest star we know today. And far below its surface is a black hole, growing rapidly as it devours billions upon billions of tons of matter per second. Normally, stars are born from gigantic clouds, collections of thousands or millions of solar masses of mostly hydrogen. In these clouds, matter starts to accumulate around the densest spots inside. As these spots get denser, their gravitational pull intensifies and they grow faster. Eventually, they generate so much heat and pressure that they ignite fusion reactions and a new star is born. But this puts a limit on their size. Nuclear fusion releases enough radiation energy that the surrounding gas cloud is blown away. The new baby star can't gather more mass. From now on, the star is living on the edge between two forces: gravity pulling in, trying to squash the star, and radiation created by fusion pushing outwards, trying to blow the star apart. After millions or billions of years, the core runs out of fuel and the balance breaks, destroying the star. But black hole stars were very, very different. The beasts of the early universe. A few 100 million years after the Big Bang, when the universe was much smaller, all the matter in existence was much more concentrated. The universe was much denser and hotter. Dark matter was a dominant player, forming giant structures called dark matter halos. These dark matter halos were so massive that they pulled in and concentrated unimaginably gigantic amounts of hydrogen gas becoming the birthplaces of the first stars and galaxies. Epic clouds of hydrogen formed, some as massive as 100 million suns, more than the mass of small galaxies. In this unique environment that will never exist again, the enormous gravitational pull of the dark matter halos drew gas into its center and created extremely massive stars. As we said before, when a star is born, it blows away the gas cloud that created it. But these titanic gas clouds in the early universe were so large and massive that even after their birth, more and more gas piled on the newborn star, making it grow to unbelievable proportions. The young star is forced to grow and grow and grow, getting more and more massive until in some cases it reaches up to 10 million times the mass of our Sun. Crushed by gravity, its core gets hotter and hotter, desperately pushing outwards, trying to blow itself apart, but to no avail. There's too much mass and too much pressure. The balance is impossible to uphold. Like a supernova on fast forward, the core gets crushed into a black hole. Normally that would be the end. Today's stars go supernova, a black hole forms, and things calm down. But in this case, the star survives its own death. A tremendous explosion rocks the star from the inside, but it's not enough. The star is so large and massive that not even a supernova can destroy it. But now it has a black hole for a heart. It's tiny, a few tens of kilometers in the center of a thing the size of the solar system. The monster grows. Stars are born from ever faster spinning and collapsing gas, and so they also spin. When a black hole is born from the core of a star, it keeps its angular momentum. This means that matter that gets drawn in doesn't just fall in a straight line, but instead begins orbiting the black hole, in smaller and smaller circles, going faster and faster. The result is an accretion disk where gas orbits at nearly the speed of light. Only a small amount of gas actually falls in at any given moment. Basically, black holes put a lot of food on the table and only nibble at it. But the matter trapped in the accretion disk doesn't have a good time. Friction and collisions between particles heat it up to temperatures of millions of degrees. Actively feeding black holes have accretion disks that are incredibly hot and powerful. This heat from the disk further restricts how much a black hole can devour, just like the core of stars. The superhot material creates radiation that blows away most of the food within its reach. So even if a black hole had access to as much food as it desired, it can only grow slowly. A black hole embedded inside a black hole star is different. The enormous pressure surrounding it pushes down matter directly into the black hole, overcoming all restrictions on how fast it can consume. This process is so violent and releases so much energy that the accretion disk becomes hotter and releases more radiation pressure than any star core ever could. Enough to push back against the weight of 10 million suns. An impossibly dangerous balance has been created. Millions of solar masses pushing in, the angry radiation of a force-fed black hole pushing out. For the next few million years, the black hole star is consumed from within. The black hole grows to thousands of solar masses, and the bigger it gets, the faster it eats, which heats up the star even more and causes it to expand. In its final phase, the black hole star has become over 30 times wider than our solar system, truly the largest star to ever exist in the universe. The intense magnetic fields at its core spew out jets of plasma from the black hole's poles, which pierce through the star and shoot out into space, turning it into a cosmic beacon. It must have been one of the most awe-inducing sights to ever exist in the universe. But this also marks the end. It becomes too stretched, and the accretion disk within too powerful. The parasite destroys its host, blowing it apart. A black hole with the mass of 100,000 suns rips its way out to hunt for new prey while leaving behind nothing but a star carcass. The supermassive question. If black hole stars existed, they could explain one of the greatest mysteries of the universe. The supermassive black holes we see at the center of galaxies are just too big. They shouldn't be possible. Black holes born from regular supernovas can be a few tens of solar masses at most. And because of the process we explained before, they grow slowly after that. If black holes merge, they can form slightly larger black holes of over 100 solar masses. It should take billions and billions of years to make black holes with hundreds of thousands or even millions of solar masses. And yet, we know that some supermassive black holes already had 800 million solar masses only 690 million years after the Big Bang. Black hole stars are a sort of black hole cheat code. If they formed very early in our universe, and the black holes that emerged from them were thousands of solar masses, then they could be the seeds for supermassive black holes. These seeds could take root in the center of the earliest galaxies, merging with others and drawing in enough matter to grow quickly and reliably. Very soon, we may be able to verify their past existence. The James Webb Space Telescope is turning its sensors to explore the farthest reaches of the universe, looking back in time, back to the early universe that we couldn't see before. So, with luck, we might be able to witness glimpses of these tragic titans in the brief moment between their formation and destruction. Until then, let's do the visual journey again, just for fun. Stars are big. Black hole stars, bigger. The largest things in the universe are black holes. In contrast to things like planets or stars, they have no physical size limit and can literally grow endlessly. Although in reality, specific things need to happen to create different kinds of black holes, from really tiny ones to the largest single things in the universe. So how do black holes grow? And how large is the largest of them all? This video will not discuss how black holes work or how they form, since we've looked at that in detail in our black hole and neutron star series. You can check them out afterwards. For now, we're interested in finding the largest thing in the universe. Let's start really small. Primordial black holes. The smallest kind of black holes may or may not exist. If they do, they're probably the oldest objects in the universe, older even than atoms. They would have formed just after the Big Bang, when the universe was so dense with violent energy that any tiny pocket that was just slightly more dense than its neighbors could produce a black hole. The smallest primordial black hole that could still be around would be 8 trillion kilograms or so, the mass of a big mountain. And yet they would be no bigger than a proton. A primordial black hole with the mass of Earth would barely be larger than a coin. This makes them very hard to find, so we haven't actually observed any yet. If they exist, they may even be the mysterious dark matter that holds galaxies together. Let's move on to the kinds of black holes that we know for sure are out there. Stellar black holes. To make a black hole, we need to compress enough matter so that it collapses into itself. After that, the more mass we throw at it, the larger it becomes. In today's universe, only the most violent cosmic events can create the necessary conditions, such as the merger of neutron stars or when the core of a very massive star collapses in a supernova. To have a unit to work with here, we'll use the mass of our Sun, about 2 million trillion kilograms. The smallest known black hole has 2.7 times the mass of the Sun, which works out as a sphere around 16 kilometers in diameter, large enough to cover Paris. Another lightweight black hole is the companion to the V723 Mon red giant star. This star is 24 times larger than our Sun, 30 million kilometers in diameter. And yet, it's thrown around by a tiny black hole just 17.2 kilometers wide. This tiny thing bullying the star is so much smaller that we can barely even show them in comparison. One of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit. As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our Sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica. To grow much larger, black holes have to either devour a lot of stars or, better, merge with one another. The instruments that make it possible to detect these mergers are very new, so we're currently discovering a lot of exciting things. Like two massive black holes that we detected in a galaxy 17 billion light-years away. As they spun around each other violently, they released more energy in the form of gravitational waves than the combined light from all the stars in the Milky Way in 4,400 years. The new black hole they formed is about the size of Germany and is 142 solar masses. And here we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time. Until we suddenly hit black holes that are millions of times more massive. Which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to explain their existence today. The universe is simply not old enough for these supermassive black holes to have formed by eating stars and merging with each other. Something else must have happened. To explain how we got the largest black holes in the universe, we might need the largest stars that ever existed, quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our Sun is like a grain of sand next to them. We don't know if quasi-stars actually existed, but they're an interesting concept when it comes to supercharging black hole development. The idea is that the matter in the early universe was so dense that quasi-stars could grow to thousands of times the mass of our Sun. The cores of these stars might have been crushed by their own weight so much to actually collapse into black holes while the star was still forming. In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. And so these quickly growing black holes might have been able to consume the quasi-star for millions of years and grow far bigger than any modern stellar black hole. Black holes several thousand times the mass of the Sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes. So now we arrive at the kings of our universe, the largest single bodies in existence. The centers of most galaxies contain a supermassive black hole, and they are monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar masses that is calm and collected and just does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass, its radius is still only 17 times our Sun. Smaller than most giant stars, but millions of times more massive. Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the Sun in the solar system. An anchor that glues everything else together and forces it into an orbit. But this is a misconception. While the Sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their galaxy. The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the gravitational effect of dark matter which holds them together. Many supermassive black holes aren't gentle giants, especially when they're feeding on the clouds of mass in their galaxy. The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 115 times larger than our Sun in the sky, and we'd be burnt to a crisp in seconds by its glowing hot accretion disk. At this point, black holes become so large that stars seem ridiculously tiny compared to them. The Galaxies Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our Sun, it would swallow all the planets and stretch halfway to the edge of our solar system. It's devouring so much mass and material that it churns its disk into a kind of magnetic funnel, spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light-years in diameter. That's 2.5 Milky Ways wide. Another pretty large supermassive black hole sits in the galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo of, or rather of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large that it covers our entire solar system. And yet, there is a scale even above these kinds of objects: ultramassive black holes. Now we reach the most massive black holes, perhaps the largest single bodies that will ever exist. These black holes have eaten so much that they've grown to tens of billions of solar masses, their gravity the engine for a quasar, an accretion disk shining brighter than thousands of galaxies full of stars. So massive that they deserve a title of their own: ultramassive black holes. The ultramassive black hole at the center of galaxy OJ287 is 18 billion solar masses. It's so big that it has a supermassive black hole nearly 40 times larger than Sagittarius A star orbiting it. This thing defies imagination and is really hard to compare to anything. It can comfortably fit 3 solar systems side by side inside of it. Let's end this insane competition and get to the King of Kings. TON 618, a black hole that we can observe consuming galaxies worth of matter, is shining with the brightness of 100 trillion stars, visible from 18 billion light-years away. It has an incredible 66 billion solar masses, a black hole so large that it would take light a week to reach the singularity after crossing the event horizon. About 11 solar systems could sit inside of it, side by side. It may very well be the largest single body in the universe, but in reality, it's probably even larger. Since TON 618 is so far away, we only see what it looked like 10 billion years ago. In any case, black holes are scary and mysterious and gigantic. They'll be here after everything else dies and growing larger and larger. Okay, now let's do the trip again. From the smallest possible black hole all the way up to the largest. Let's try something new today. We can call it Behind the Lies, a short behind-the-scenes bit about the necessary inaccuracies in this video, because it's not really actually possible to rank black holes like trading cards. How so? Well, while we've catalogued millions of stars, we really only have good data on a couple of dozen black holes. That's because black hole gazing wasn't really a thing until 50 years ago, and technically still isn't because we can't see black holes. We can only derive their properties from studying their gravitational effects on the matter around them, like the orbit of stars that come close to them. This effect depends on the mass of the black hole, which we can approximate at the most basic level with Kepler's laws. But this comes with huge uncertainties and error bars. Then we have to convert mass to size next, which brings new uncertainties. For example, we calculated the radius from the mass using the Schwarzschild equation, which for the sake of simplicity assumes black holes are perfectly round and don't spin, a kind of black hole that doesn't really exist. The reality is that physics on these scales is a bit fuzzy. So some of the black holes we talked about here may be way smaller or way bigger. We just don't know for sure. We shimmied around this problem by comparing different sources with different kinds of values and using different mass calculations to arrive at a standardized list that allowed us to be as accurate as humanly possible. You can look at all of this in our source doc. As a result, this script was written with the tears of experts we drove crazy with our obsession for the best values they could live with. In this process, tons of stuff got cut and didn't make it into the final video. But luckily, we found a way to not waste all of it. We've created a lot of black hole merch, spanning the whole range from somewhat bonkers to more serious. This way, we get to explore a topic from different angles, and you get to continue having fun with black holes after this video ends. Casually watching a video on YouTube on a computer more powerful than anything humanity could build a few decades ago. This progress and all the wonderful machines you take for granted are built on a few rare and precious materials with names like terbium, neodymium, or tantalum. Getting these rare materials from the ground into your devices is ugly. The mining industry is responsible for air and water pollution and the destruction of entire landscapes. Dangerous chemicals like cyanide, sulfuric acid, or chlorine are used to extract the resources, harming biodiversity, workers, and locals. And rare resources are also political tools when countries restrict access to them to get their way. But what if we could replace the mining industry on Earth with a clean process that can't harm anyone? Well, we can. All we need to do is look up. Asteroids are millions of trillions of tons of rocks, metals, and ice, leftovers from the cloud that became the planet 4.5 billion years ago. They can be as small as a meter or protoplanets the size of entire countries. Most of them are concentrated in the asteroid belt and the Kuiper belt, while hundreds of thousands more do their own thing between the planets. As space travel is becoming more feasible, scientists and economists have begun looking at the resources found in these asteroids. Even relatively small metallic asteroids may contain trillions worth of industrial and precious metals like platinum. And bigger asteroids like 16 Psyche could contain enough iron-nickel to cover the world's metal needs for millions of years. At current market prices, the rare raw materials alone would be worth quadrillions of dollars. Well, not really, but technically. For example, there are more than 20 million tons of gold in the ocean's water, worth roughly $750 trillion US, but filtering out the gold would be so expensive that you'd lose money selling it. Right now, asteroid mining has exactly this problem. It's too expensive to replace mining on Earth. Billions of dollars worth of valuable resources in space are worthless if it costs trillions to get them. What makes it so hard? The principles behind mining an asteroid are simple. The basic idea is to choose an asteroid, move it to a place where it's easy to process, and then take it apart to turn into useful products. Unfortunately, all of this collides with fundamental problems humans have yet to solve. Going to space is expensive. It costs thousands of dollars in rocket fuel for each kilogram just to reach a low Earth orbit. Going further out into deep space costs thousands more. We need cheaper space travel to make asteroid mining profitable. One solution is to switch from classical rockets to electric spaceships. We already use electrical rocket engines for many of the space probes on science missions. In principle, we only need to build bigger ones. While electrical engines are not powerful enough to fly to space, they require only a tiny amount of fuel to go very far once they're in space. This means we don't need to spend a lot of money on fuel only to transport fuel into space. This doesn't solve the whole cost problem, but it makes it easier to start our first mission. Now that we have an electric asteroid mining spaceship, we need to find the right asteroid and get it there. We've already successfully visited asteroids with space probes and even collected samples. Still, to make it easier and cheaper, our first targets will probably be near-Earth asteroids. Asteroids that orbit, well, near Earth. After a few months of travel, our spaceship finally arrives at our asteroid. Weirdly formed, littered with small impact craters, it hasn't changed much for billions of years. The first thing that needs to be done is to secure the asteroid and stop it from spinning. There are multiple ways to do this, like vaporizing material with a laser or stopping the rotation with thrusters. Once we have a stable asteroid, we need to wait. Orbital mechanics are complicated, but if you push something in the right direction at exactly the right moment, you can move very big things with very little force. So we wait for exactly the right moment. Our ship fires its thrusters and nudges the asteroid into a trajectory that takes it near our moon. The moon is useful because we can borrow its gravitational pull to put the asteroid in a stable orbit around Earth, which saves even more fuel. Again, the trip takes months. But all the time since our ship was launched has not been wasted. The first space mining and processing equipment has been installed in orbit and is now carefully moving towards the asteroid. The processor works very differently than on Earth. Giant mirrors focus sunlight and heat up asteroid rock to boil out the gases. Grinders break up the dried rocks into gravel and dust, and centrifuges separate dense from light elements. Even if we only extract 0.01% of the asteroid's mass in precious metals, this is still several times more than you'd get from the same amount of ore on the ground. But what now? How do we get our precious metals safely back to ground? There are a few ways, like loading it into reusable rockets that return to Earth from space. Or if our processor contains 3D printers, we can print a faster and cheaper delivery system. Heat-shielded capsules filled with gas bubbles. These can just be dropped into the oceans where ships tow them away. This could be the starting point of humanity's first real steps towards colonizing the solar system. As our infrastructure and experience grows, our missions get more and more sophisticated. Parts and fuel produced on asteroids don't have to be launched from Earth at all. The first mining operation makes the second one easier, and so on. While the space industry grows and precious materials become cheaper, eventually we could stop mining on Earth. Even the idea of toxic mining down here might become something weird and anachronistic, like having an open fire in your living room. Landscapes ravaged by pollution will heal, while the technological wonders we're used to get cheaper and less toxic to make. None of this is science fiction. We don't need fancy materials or new physics to make asteroid mining happen. We could start building this future today. All we need is an initial push. Black holes are the most powerful things in the universe, strong enough to rip whole stars into atom-sized pieces. While this is scary enough, they have an even more powerful and dark property: they might delete the universe itself. Black holes in a nutshell. A black hole appears when an extraordinary amount of matter is concentrated in a tiny space. At their center, gravity is almost infinitely strong, and whatever gets too close is ripped into its elementary particles. Not even light can escape black holes, and so we perceive them as spheres of blackness. If you were to fall into a black hole, nothing bad would happen until well after you crossed its outer border, the event horizon. You can imagine this as swimming in a river that ends in an enormous waterfall. As you float along, imperceptibly, the stream gets faster and faster, even if you can't see the waterfall yet. You could swim to safety until, without even noticing it, you cross the point of no return. No matter how fast you try to swim now, the stream will pull you towards certain death. Nothing can escape a black hole waterfall once it gets too close. This border completely separates black holes from the rest of the universe. We can't access them unless we're willing to never return. So there's no way of telling what's really going on inside black holes, but we have a few ideas about what's going on right at their very edges. Black holes radiate their mass away, like a hot pot on a stove losing its water as steam. This is called Hawking radiation. Black holes constantly lose an extremely tiny amount of their mass, a process that's unbelievably slow. It will take a black hole with the mass of our Sun 10,000 billion years to lose 0.0000001% of its mass. This is happening constantly and unstoppably, and as it goes on, it speeds up more and more. In the far, far future, when the last star in the universe has been dead for trillions of years, black holes will become tinier and tinier until they evaporate and disappear, leaving behind just a bit of radiation. But this is a problem, because in the process of disappearing, black holes might delete something fundamental: information. 2. What is information? Information is nothing tangible. It's typically understood as a property of the arrangement of particles. What does this mean? Imagine a bunch of carbon atoms. Arrange them in a certain way and you get coal. Arrange them in a different way and you get a diamond. The atoms are the same. What changes is the information. If we make this more complex and add in a few more atoms, we get a banana. Change the arrangement of the atoms, and we get a squirrel. The basic building blocks of everything in the universe are the same and don't care if they're part of a bird, or a rock, or a cup of coffee. Without information, everything in the universe would be the same. According to the theory of quantum mechanics, information is indestructible. It might change shape, but it can never be lost. For example, if you burn a piece of paper, you get ash. That ash will never become paper again. But if you were able to carefully collect every single carbon atom in the ash and measured the exact properties of the smoke and heat radiating from the fire, you could, in theory, reconstruct the paper. The information of the paper is still in the universe. It's not lost, it's just hard to read. If you could somehow measure every single atom and particle and wave of radiation in the universe, you could see and track every bit of information there is. Hypothetically, you could see the entire history of the universe right back to the Big Bang. And here, black holes trip us up. Information tells us how things are different from each other and what used to be what. Black holes do the opposite. They take different things and make them the same. They destroy information. This creates the information paradox, and this is a serious problem. The information paradox. It's fundamental for all our laws of physics that information can never be lost. Existing, not existing, without information, everything is relative. When it comes to our understanding of reality, we need absolutes. How could we solve this paradox? There are a few possibilities. 1. Information is lost, irretrievably and forever. This means we have to nix all our laws of physics, throwing out a lot of stuff that's worked very well so far and start from scratch. What those new laws of physics would look like, or what that means for us, nobody knows. This is a little frightening, but also kind of exciting. 2. Information is hidden. Maybe a little part of the black hole splits off and forms a baby universe. The information would be transferred into this new, weird place where we could never observe or interact with it, but technically it would not be lost. It's like having a broken hard drive with all your family photos that you could never access. Sure, it's nice that they've not been deleted, but also not very helpful. Or maybe black holes don't disappear completely after the end of their life cycles, but a little piece is left, an information diamond. Like a clown car filled with an infinite amount of information clowns. But there's a third option: information is safe after all, not lost or hidden. Perhaps we've just been looking at this whole thing the wrong way. We know that black holes trap information and might delete it later, but we never thought about what they do with it in the meantime. Where do black holes store their information? Cosmic housekeeping. Let's create a black hole with dirty laundry. First, we fill up a room with laundry baskets. The more laundry you want to store, the more baskets you put in the room. But at some point, every single basket is full and the room is completely stacked. Not a single extra sock fits in. The room is at maximum capacity. But if we still squeeze the sock in with a lot of energy and violence, the room collapses in on itself and forms a black hole. But the capacity of the room itself has not changed. Fitting in more stuff or information is still impossible. So what happens if we throw more laundry into it? The room itself gets a little bit bigger to make space for the new information. It turns out a black hole grows its surface by a tiny pixel for each bit of information we throw into it. In a nutshell, more information means more surface area. The information gets painted on the surface, similar to what happens when we throw a stone into a pond. After the stone sinks to the bottom, we can't see it anymore, but we can tell that something went in from the ripples on the surface of the pond. Even the smallest black hole can store more information on its surface than all the data ever produced in human history. They do this by storing information in a type of pixel that is unbelievably tiny. Black holes are the ultimate hard drive. This is a bit like taking a paperback and turning it into an ebook. Two things that look completely different, but their content is the same. It's just encoded and memorized in another way. Black holes swallowing stars and planets is a bit like transferring a whole library onto an e-reader. This solution is called the holographic principle. But if it's correct, then everything we thought we knew about the universe is wrong. The universe is a hologram. If information is actually stored on the boundary of a black hole, the Hawking radiation has a chance of learning about the information encoded there and can carry it away. So, information is not lost when black holes fade away, and we do not need to redo physics. The information paradox is resolved. But we still have to change our understanding of reality in a fundamental way. If everything that falls into the black hole is stored on its event horizon, that basically means that three-dimensional stuff is encoded on a flat surface. We have a name for this, a hologram. A hologram is like a 3D photo, a flat piece of plastic that encodes a three-dimensional image. A black hole is like a hologram because everything inside it is encoded on its event horizon. A person inside a black hole would experience their usual three-dimensional life. But for us on the outside, they are flattened images on the surface of the black hole. The consequence of this is counterintuitive, but stay with us for a moment. Black holes are very extreme objects, but they're still bound to the same rules as everything else. So if this crazy duality between 2D and 3D works for black holes, then it might work for the whole universe and you in it. Since a person inside a black hole would not realize that they're encoded on a flat surface, we might share the same fate. You really might be stretched over a flat screen at the end of the universe. The science behind this is complicated and really weird, with toy universes to play with, string theory, and a lot of maths. We'll talk about this more in another video. Regardless of what the true nature of the universe really is, we just know that it's strange and complicated, and we have to do a lot more physics to understand it. But black holes might be key to understanding the nature of reality itself. One day the universe will die, but why and how? And will the universe be dead forever? And how do we know that? First of all, the universe is expanding, and not only that, the rate of its expansion is accelerating. The reason? Dark energy. Dark energy is a strange phenomenon that scientists believe permeates the universe. Until 1998, we thought that the universe must work a bit like a ball that you throw into the sky. The ball moves up, but at some point it has to come down again. But the expansion of the universe is actually speeding up. That's like throwing a ball up and watching it fly away faster and faster and faster. Where is this acceleration coming from? Well, we don't know, but we call it dark energy. Einstein thought of it first and then decided it was stupid. Now, astrophysicists have decided it is plausible. Trouble is, this is all very theoretical, and we don't actually know what the properties of dark energy are. But there are various theories, and they lead us to three scenarios for the end of the universe. 1. The Big Rip. Since its birth, the universe has been expanding. For unknown reasons, new space is created everywhere equally. The space between galaxies expands, so they move apart. The space inside galaxies also expands, but here gravity is strong enough to keep them together. In the Big Rip scenario, the expansion accelerates up to a point where space expands so fast that gravity can't compensate for this effect anymore. The result is a Big Rip. At first, only large structures like galaxies are torn apart since space between the single objects expands very fast. Next, big bodies like black holes, stars, and planets die. Their gravity isn't strong enough to keep them together, so they dissolve into their components. In the end, space would expand faster than the speed of light. Atoms would now be affected, and they would just disband. Once space is expanding faster than light, no particle in the universe can interact with any other particle anymore. The universe would dissolve into countless lonely particles that won't be able to touch anything else in a strange, timeless universe. And you thought you felt lonely. 2. Heat death, or a big freeze. In a nutshell, the difference between the Big Rip and heat death is that in a heat death scenario, matter stays intact and is converted over an incredibly long but finite period of time into radiation while the universe expands forever. But how does this work? Let's talk about entropy. Every system tends towards the state of highest entropy, like when we have a latte macchiato. Initially, it has different regions, but over time they will cool down and disintegrate until it's uniform. And this also applies to the universe. So while the universe gets bigger and bigger, matter slowly decays and spreads out. At some point, after lots of generations of stars, all the gas clouds necessary to form stars will be exhausted, so the universe will turn dark. The remaining suns will die. Black holes will slowly degenerate and evaporate over trillions of years due to what's known as Hawking radiation. When this process is complete, only a dilute gas of photons and light particles remains until even this decays. All activity in the universe ceases at this point. Entropy is at its maximum, and the universe is dead forever. Unless, theoretically, it might be possible that after an incredibly long amount of time, there might be a spontaneous entropy decrease as a result of something called quantum tunneling, leading to a new Big Bang. 3. Big Crunch and Big Bounce. This is the most uplifting scenario. If there is less dark energy than we think, or it decreases over time, gravity will be the dominating force in the universe one day. In a few trillion years, the rate of expansion of the universe will slow down and stop. After that, it reverses. Galaxies will race at each other, merging as the universe becomes smaller and smaller. Since a smaller universe also means a hotter universe, temperatures rise everywhere all at once. 100,000 years before the Big Crunch, background radiation would be hotter than the surfaces of most stars, which means that they would be cooked from the outside. Minutes before the Big Crunch happens, atom cores are ripped apart before supermassive black holes devour everything. Finally, all black holes would merge into a supermassive mega black hole that contains the entire mass of the universe, and in the last moment before the Big Crunch, it would devour the universe, including itself. The Big Bounce theory states that this has happened a lot of times and that the universe goes through an infinite cycle of expansion and contraction. Well, wouldn't that be nice? So what will actually happen to the universe in the end? At the moment, heat death seems the most likely, but we at Kurzgesagt hope that this dead forever stuff is wrong and the universe will start over and over again. We don't know for sure either way, so let's just assume the most uplifting theory is true. Life has existed on one planet for about 4 billion years as far as we know, but it might have started right after the Big Bang, when the universe was much stranger and more fantastic than today. A universe that might have allowed life to develop absolutely anywhere. The cosmos might be full of the seeds of life, sleeping in a dead desert, waiting for a few drops of rain to explosively bloom and grow. Tiny and not so tiny aliens might be everywhere. In this video, we're going to put together two highly speculative yet scientifically grounded possibilities. Check out the scientific papers in our sources. To properly explain it, let's first look at the paradox of life on Earth. The life paradox. For its first few 100 million years, Earth was a magma hell, constantly bombarded by asteroids. But basically, the second things calmed down and the first oceans formed, life just appeared, and zillions of microbes settled every nook and cranny they found. This is kind of strange. Life on Earth seems to be almost as old as the planet itself, as if it was waiting around for an opportunity. But life didn't only appear extremely quickly. In that tiny time window, it also crossed a huge gap. To qualify as living things, even microbes need to eat, poop, grow, and multiply. To do that, they need a genome, the biological instruction manual that sets the inner workings of an organism. How dead things with no genome become living things with genomes is one of the biggest riddles of science. Simplifying a lot, the problem is that to have a functioning genome, you need proteins, and to make those proteins, you need a functioning genome. Both proteins and genomes are super long molecules made of pretty complex blocks that are extremely difficult to assemble by chance. It's a chicken-egg paradox with several chickens and eggs. Once you have a finished cell, the whole system works efficiently. But starting from simple dead stuff and reaching that level of sophistication by pure chance should require an amazing amount of time for trial and error. So how did the first living things manage to cross that gap in just a few 100 million years? Most theories about the origin of life try to explain that gap by theorizing how some primitive soup of prebiotic molecules could have efficiently produced the first self-replicating entities. But we still don't know how exactly this would have worked. Maybe we need to think backwards. The clock of evolution. Think of genomes as a book telling the history of life. As time passed and life evolved, more characters were introduced. Amoeba, fish, amphibians, dinosaurs, and mammals. Over billions of years, the story of life got more and more complex. A genome can be viewed as a long string of letters with biological instructions. And from microbes to us today, functional genomes seem to have been increasing in size at a fairly constant rate. The functional genome of fish is more than twice that of worms. Our functional genome is about twice bigger than that of fish, and so on. It is a bit more complicated, but for now, let's run with this. When we put all these clues together, it seems that genomes have been doubling in size on average every 350 million years or so, as if evolution had been following an exponential inner clock. But it gets even stranger. The very first microbes that emerged on Earth, even if they look simple, already seem to have had pretty long and complex genomes. But how could life have achieved that level of complexity in such a short time? There may be an interesting way to solve this riddle. We just take our exponential clock and extrapolate it back in time to the simplest conceivable life form. Something equivalent to a being with a genome containing just a few letters. But if we do that, we end up 10 billion years in the past. More than twice the age of Earth, which means if life actually evolved like this, it didn't start here, but somewhere out there, in space. This would explain why life started to thrive so quickly on our young planet. If it was already present in space like a seed, it just needed water and warm temperatures to wake up and go on evolving. And it would also explain the high degree of sophistication of the first life forms on Earth. They could have been complex already because they might have been evolving for billions of years somewhere else in the universe. But could life really be that old? Maybe, yes. Actually, life could have started shortly after the universe itself was born. A Goldilocks baby universe. At its most basic level, life needs two things: the right chemical elements to form complex molecules and a liquid medium, like water, in which those molecules can move and interact. The liquid medium needs to stay warm enough to remain, well, liquid. So when we search for life in space, we focus on Earth-like planets at just the right distance from their star, warm enough to sustain liquid water. But there was actually a time when almost all of the universe might have been habitable. Right after the Big Bang, the universe was extremely hot. But as the cosmos expanded, it cooled. And between about 10 and 17 million years after the Big Bang, when the universe was 1,000 times younger than today, it was between 100 degrees Celsius and 0 degrees Celsius, the temperature at which water is liquid. So for this window of time, more than 13.7 billion years ago, the whole universe, absolutely every inch of it, had the right temperature to support life. Of course, the right temperature alone is not enough for life. We also need chemical elements like carbon and oxygen, which are forged in the cores of stars. But were there stars in super early cosmic times? Maybe, yes, in regions of the universe where matter was especially dense. Such stars would have been very massive and gone supernova in just 3 million years, seeding the baby universe with the chemical elements needed to form dust, asteroids, planets, and the ingredients of life. Maybe the first ancestors of life were more exotic and didn't even need water, but thrived in substances like ammonia or ethane that can stay liquid at temperatures far below 0 degrees Celsius. They could have been sustained by the lingering warmth of the Big Bang for tens of millions of years longer, well into a time when we know for sure there were stars and all the chemical elements. The real magic of this idea is that while the universe today is extremely deadly and hostile, back then the conditions for life might have been basically everywhere. For a period that may have lasted several dozen million years, primordial life might have been able to emerge on any rock, even between the stars, sowing the universe with the seeds of what, billions of years later would become bacteria, trilobites, dinosaurs, and finally us. At some point, the universe cooled down below the right temperature for life to thrive, but some of those ancestral life forms may have continued to exist in the internal warmth of the first planets, frozen in asteroids or hibernating in cosmic dust. Tiny seeds roaming the cosmos, waiting for new hospitable places to continue evolving. If they did, life now might be everywhere in the universe. Will we ever know? All this makes for a nice story. And while both the habitability of the baby universe and our exponential clock of life are reasonable ideas, they're still speculative. One more possibility among many others trying to explain our existence today. But if life came to Earth from outer space, then it should have seeded other places in the solar system too. Maybe there are fossils in dry riverbeds on Mars. Maybe we'll soon find life in the warm underground oceans of Enceladus or Europa. Titan has seas, rivers and lakes of ethane and methane as warm as the universe when it was 90 million years old. So finding exotic life on Titan would support the idea that life could have originated in the weird baby universe. So far, when we look out into the cosmos, we don't see anyone like us. But maybe that's because life needed 10 billion years or more to reach the level of complexity that allows for a technological species. Maybe there are millions of worlds filled with microbes, oceans full of exotic fish, and continents of bizarre animals. And maybe even others like us that just recently gained consciousness and are beginning to look at the sky, wondering if they're alone. Life could be flourishing right now in uncountable forms and in all kinds of cosmic environments. And if many of us share a common cosmic origin, we would all be part of a great cosmic family. The answer may lie in our cosmic backyard. Let's go and find out. Neutron stars are the densest things that are not black holes. In their cores, we might find the most dangerous substance in existence: strange matter. A bizarre thing so extreme that it bends the rules of the universe and could infect and destroy everything it comes into contact with. Or it could teach us about how the universe began. Maybe both. To understand how extreme strange matter really is, we first need to get a few basics. What is a neutron star, and how does strange matter break the rules of the universe? To get all of this into one video, we'll grossly oversimplify a few things, but we'll provide you with further reading if you want more details. A neutron star is what remains after a very massive star explodes in a supernova. When this happens, the star's core collapses under its own gravity with such a strong inward force that it squeezes nuclei and particles together violently. Electrons are pushed into protons, so they merge and turn into neutrons. All the nothing inside of atoms is suddenly completely filled with particles that really don't want to be close to each other but have no choice. They desperately push back against gravity, against the collapse. If gravity wins, they will become a black hole. If they win, they become a neutron star. This makes neutron stars like giant atomic nuclei the size of a city, but holding the mass of our Sun. And here, things get weird. The environment in the core of neutron stars is so extreme that the rules of nuclear physics change. And this could lead to a strange and extremely dangerous substance. But let's not get ahead of ourselves. We first need to know the rules before we learn how they can be broken. Protons and neutrons, the particles making up the nuclei of atoms, are made up of smaller particles called quarks. Quarks really don't want to be alone. They are what we call confined. You can try to separate them, but the harder you pull, the harder they try to pull themselves back together. If you use a lot of energy, they just use this energy to create new quarks. Quarks only exist together as the building blocks of other particles and have never been observed by themselves. They come in many types, but only two appear to make stable matter: the up and down quarks found in protons and neutrons. All other quarks seem to decay away quickly. But this may be different inside neutron stars. The forces operating in their cores are so extreme that they are actually similar to the universe shortly after the Big Bang. neutron star cores are like fossils, which can let us peer back in time to the beginning of everything. So learning how quarks behave inside a neutron star is a way of understanding the very nature of the universe itself. One hypothesis is that inside a neutron star core, protons and neutrons deconfine. All the particles crammed shoulder to shoulder dissolve and melt into a sort of bath of quarks. Uncountable numbers of particles become one giant thing made purely from quarks, quark matter. A star made from this is called a quark star, though from the outside it may not look any different than a regular neutron star. Now we can finally talk about the most dangerous substance. If the pressure inside a quark star is great enough, it may get stranger. Literally. In the cores of neutron stars, some of the quarks may be converted into strange quarks. Strange quarks have bizarre nuclear properties, and they are heavier and, for the lack of a better word, stronger. If they turn up, they could create strange matter. Strange matter might be the ideal state of matter. Perfectly dense, perfectly stable, indestructible. More stable than any other matter in the universe. So stable that it can exist outside neutron stars. If this is the case, we have a problem. It might be infectious. Every piece of matter it touches might be so impressed by its stability that it would immediately turn it into strange matter too. Protons and neutrons would dissolve and become part of the quark bath, which frees energy and creates more strange matter. The only way to get rid of it would be to throw it into a black hole. But then again, who cares? All of it is inside neutron stars. Except when neutron stars collide with other neutron stars, or black holes, they spew out tremendous amounts of their insides, some of which could include little droplets of strange matter called strangelets. Strangelets are as dense as the core of a neutron star. They could be really small, maybe even subatomic, but even the largest strangelets wouldn't be any bigger than a rocket. These strangelets would drift through the galaxy for millions or billions of years until they meet a star or planet by chance. If one were to strike Earth, it would immediately start converting it into strange matter. The more it converts, the more it would grow. Ultimately, all of the atoms making up Earth would be converted. Earth would become a hot clump of strange matter the size of an asteroid. If a strangelet strikes the Sun, it would collapse into a strange star, eating through it like fire through a dry forest. This would not change the Sun's mass much, but it would become way less bright, so Earth would freeze to death. And like a tiny virus, we'd have no way to see a strangelet coming. Worse still, some theories suggest strangelets are more than common, outnumbering all stars in the galaxy. These strangelets could have formed very early after the Big Bang, when it was as hot and dense as a neutron star core everywhere. They might be clumping around the gravity of galaxies as the universe expanded and evolved. Strangelets could even be so numerous and massive that they might actually be the dark matter we suspect holds galaxies together. But then again, maybe not. This is speculation, and the Earth and Sun and planets haven't been consumed in a wildfire of strangelets in the past few billion years, so the odds seem good that it won't happen anytime soon. Understanding these strange objects today may be the key to understanding the birth of our universe and why it grew to look the way it does now. When scientists first started playing with magnets and wires and thinking about electrons, they had no idea how technology would evolve in the next 100 years. The scientists thinking about the cores of neutron stars and strange matter today may be setting up humans for a future beyond our wildest imaginations. Or maybe not. Time will tell. Humans dream about leaving Earth and traveling through the galaxy, but we were born too early to be part of it. Or were we? The reality is, we could begin our dream by building a moon base today. We actually do have the technology, and current estimates from NASA and the private sector say it could be done for $20 to $40 billion spread out over about a decade. The price is comparable to the International Space Station or the budget surplus of Germany in 2017. Not that big an investment, really. The payoff would be immeasurable. The moon is a sandbox to develop new technologies and exploit unlimited resources. It would start a new space race and lay the foundation for us to spread out into the solar system and beyond. It would create a vast array of new technologies to benefit us on Earth, and we would all be part of it. So why aren't we doing it? Well, sadly, it's hard to get governments interested in long-term investments in the future of humanity. Let's imagine just doing it. If we start today, how would we build a moon base? Throughout history, colonization happened in phases. In the first phase of the age of exploration of the New World, for example, European monarchs funded expeditions to chart and discover and to stake their claims. They planted a flag and set up a camp, but they didn't stay. In the second phase, small missions set up outposts and settlements were founded, which were still very dependent on their home countries for supplies. Some failed, but others survived and established a permanent presence. Only then, in the third phase, did a true colony form to which tradesmen and labourers could emigrate, creating new wealth and opportunities for themselves and their families, sending extreme wealth back to their countries of origin. When we colonize the moon, we'll go through the same three phases, this time without murdering millions of innocent people in the process. The moon is not a welcoming place for living things. A moon day lasts 29 Earth days, with a difference of nearly 300 degrees Celsius between sunlight and shade. There's no atmosphere to shield us from meteorites, big and small, or cosmic radiation. Worse still, the lunar surface is covered in a layer of nasty, jagged dust. The moon is hard, but we're good at doing hard things. In the first phase of lunar colonization, our explorers proved it can be done, that a new world can be reached. This phase started 60 years ago with the Apollo missions. Since then, satellites like the American Lunar Reconnaissance Orbiter have mapped the moon, while rovers like the Chinese Yutu have studied the composition of the lunar surface, looking for water ice and metals. Phase 1 is more or less complete. We know what we need to know to enter Phase 2. In the second phase, astronauts will build the first moon base, and this could begin today. The first small moon base could be completed in a decade. The first nation that establishes this base will be akin to the First Nations building outposts in the New World 500 years ago. It's expensive to send rockets to the moon, so we will send as little as possible. The base will be light, little more than inflatable habitats for crews of no more than 12, and will be deployed somewhere with natural shelter. Options include caves, like underground lava tube tunnels or craters near the poles where the days are 6 months long. These astronauts will not stay long. The habitat is likely to be abandoned between missions, as solar panels cannot generate electricity during the lunar night. But they'll do the groundwork to enable humans to stay permanently. Our first crew will consist of scientists and engineers who will study the composition of the moon and whose experiments will explore ways of using the available lunar material, say purifying lunar ice and turning it into water for human use. And water is important for far more than drinking. They can use it to experiment with growing plants for food. Hydrogen fuel cells will store power through the long night, extending astronaut stays. And most importantly, it can be split into hydrogen and oxygen, rocket fuel. By harvesting water from the moon and putting it into orbit, the moon base will supply an orbital depot where scientific missions to Mars and the outer solar system can refuel. Compared to the Earth, it's much easier and cheaper to get things off the moon into orbit. Colonizing Mars may mean starting from the moon. But this isn't a true colony, not yet. The base will be abandoned if funding stops. If we want our base to grow into the third phase, into a true colony, it must become self-sufficient, supporting itself via exports to Earth. Now, private contractors arrive, looking to get rich off lunar resources and support services. If it's cheaper to produce rocket fuel in space, what else can they get rich on? They could extract precious metals, abundant in impact craters, and other raw materials from the lunar regolith. One promising possibility is the mining of helium-3, an isotope that could one day be used in nuclear fusion reactors, something the Chinese lunar exploration program is currently looking into. Future colonists may export helium-3 back to Earth, providing us with cheap and clean fusion energy. Asteroids could be pulled into the moon's orbit and mined. With commercial exports to Earth, the colony is fully in its third phase, self-sufficient and economically productive. Our base will begin using lunar material in its construction projects if it's to continue growing. Fortunately, lunar soil has all the necessary ingredients to make concrete. Robotic mining rigs can sift the lunar dust for organic molecules and could be used to build huge structures way too massive to be brought from Earth, while advances in 3D printing will make it possible to produce almost everything else the crews need. It's hard to say when exactly the colony becomes self-sustaining. Growth is gradual, experiments are replaced by industry, and the population steadily reaches the hundreds, encompassing more than just scientists. Engineers, pilots, and contractors representing countries and corporations will be present. Two of these people will make a breakthrough, not scientific, but social. They will have the first extraterrestrial child. Throughout history, the birth of the first child was celebrated as a moment where the seed of a colony finally and irreversibly took root. Here, it means that the moon is not just a place for scientists and engineers to work, it's a place for people to live, to raise a family. Once this transition happens, the colony grows rapidly, building more habitats and schools and farms and all the things needed to support the growing population. As our colony grows, all kinds of new technologies will be invented to sustain it. They might develop crops that efficiently recycle carbon dioxide or that grow with very little water. They might find ways to recycle and reuse 100% of their waste, technologies that are extremely valuable for Earth. They could even build the first space elevator in the solar system. With a space elevator, spacecraft, astronauts, and raw materials could be brought back and forth from lunar orbit without needing to use rockets at all. The moon may become a hub for economic activity on a scale that's hard to imagine right now. It's hard to say who will own the colony at this point. Will the first person born on the moon take the national identity of their parents, or will a new generation meld together into a new lunar society? And when existing treaties that bar any nation from owning the moon are inevitably rewritten, will the colonists be given a say? Will they declare independence from the Earth? However it happens, the moon is a perfect sandbox to learn how to colonize the solar system, the perfect project to unify nations, and the only way to guarantee our survival as a species should something tragic happen on Earth. If we ever want to colonize the Milky Way, we'll have to start somewhere. So why not start there? Why not start now? Space travel is the most exciting and challenging adventure humanity has ever undertaken. But in an irony of history, we may stop ourselves from going into space the more we do it. With every rocket launched and with every satellite deployed, we're creating a trap for ourselves that gets deadlier and more dangerous every year. If it's ever activated, it could end the space age and trap us on our planet for decades or even centuries. Getting something into space is incredibly hard. To do so, you need to move very, very fast, at first straight up to leave the atmosphere, then sideways to begin a sort of circling around the Earth, still very, very fast. If you do that successfully, you can enter a low Earth orbit. And once in orbit, it's very hard to get out of orbit. Unless you have energy to spare, you're sort of locked in here, falling around the Earth forever. That's great for things we want to stay up, like space stations and satellites. And so we moved the majority of humanity's space infrastructure to this place, just a few hundred kilometers above the surface. Just high enough so that the atmosphere is so thin that orbiting things can stay up for centuries before air resistance can slow them enough to bring them back to Earth. But this is also the source of our deadly trap. Rockets are really metal cylinders that keep big piles of fuel in place. Whenever a portion of the fuel has been spent, the empty tanks are dropped to make the rocket lighter. Some parts crash down to Earth or burn up in the atmosphere. But most of the useless rocket parts stay up and begin to orbit the planet. After decades of space travel, low Earth orbit is a junkyard of spent boosters, broken satellites, and millions of pieces of shrapnel from missile tests and explosions. Right now, we know of around 2,600 defunct satellites, 10,000 objects bigger than a monitor, 20,000 as large as an apple, 500,000 pieces the size of a marble, and at least 100 million parts so small they can't be tracked. This debris is moving at speeds of up to 30,000 kilometers per hour, circling Earth on crisscrossing orbits multiple times a day. Orbital speeds are so fast that being hit by debris the size of a pea is like being shot by a plasma gun. On impact, the debris vaporizes, releasing enough energy to punch holes straight through solid metal. So, we've covered the space around our planet with millions of deadly pieces of destruction. And we also put a $1 trillion global infrastructure network right in the danger zone. It performs critical duties essential to the modern world: global communication, GPS and navigation, collecting weather data, looking out for asteroids, and all manner of scientific discoveries. Things we would miss very much if they suddenly went away. If just one pea-sized bullet hits one of our 1,100 working satellites, it will be destroyed instantly. 3 or 4 satellites are already being destroyed this way every year. As the number of satellites and the amount of junk in orbit is expected to grow tenfold in the next decade, we're approaching a tipping point. But the worst thing in space is not tiny pieces of junk. The worst thing would be an unstoppable chain reaction that turns a lot of non-junk things into junk. For example, if 2 satellites hit each other in just the right way. If satellites collide, they don't stop and fall out of the sky. It's more of a splash than a crash. Orbital speeds are so fast, solid pieces spray right through each other, transforming the 2 satellites into clouds of thousands of little things still fast enough to destroy more satellites. This could trigger the slowest and most destructive sort of domino effect, a collision cascade. Like a shotgun spray, each collision creates more bullets. What was once a single tiny target, very unlikely to hit anything, becomes a wall of destruction, hungry to make more. As more and more satellites are destroyed, the destruction accelerates exponentially, eventually destroying everything parked in orbit. But space is very empty, so the first few collisions may take a long time. By the time we realize what's happening, it's too late. 1 year, 1 satellite is destroyed, and that's no big deal. The next year, 5. The year after, 50, until there's nothing left. The situation in orbit is rapidly worsening, and we may already be past the point of no return. Within 10 years, space around Earth may no longer be viable for long-term satellites or rockets. The worst-case scenario is horrifying. A debris field made of hundreds of millions of pieces, many too small to track, moving at 30,000 kilometers per hour. It would effectively create a deadly barrier around Earth, possibly too dangerous to cross. Dreams of moon bases, Mars colonies, or space travel at all may be set back centuries. And the loss of our space infrastructure would send some of the technology we rely on daily back to the 1970s. But it might not be too late to clean up our mess. While the space industry has become better at avoiding space junk, it's still growing fast and occasional weapon tests don't help. So there have been a couple of wild but also serious suggestions about how to quickly remove as much deadly space junk as possible without creating more in the process. Lots of ideas are being thrown around, and some of the most seriously considered involve capture and return missions, which are being tested now. One method involves meeting a piece of junk in orbit with a small satellite loaded with a net. Once caught, a small rocket could be used to bring it down towards Earth. Targets too large for a net might be instead caught with a harpoon on a tether. Instead of firing a rocket, the cleaner would deploy a large sail to produce atmospheric drag and accelerate orbital decay. And there are lots of other wild sci-fi sounding proposals too. Some might use giant electromagnets. These magnetic tugs work by pushing on the magnetic components inside satellites that they use to stabilize and orientate themselves in Earth's magnetic field. These may be safer and more reliable than nets and harpoons because they never have to make contact with the junk they're handling, so there's no risk of accidentally breaking up their target into more junk. As for the tiniest bits of junk, lasers might be the key to vaporizing them entirely. Satellites with lasers wouldn't need to visit their targets, they can shoot them from far away. Large objects can't exactly be shot down, but lasers can be used to ablate them or burn tiny amounts of material off the side to push the junk to a safer orbit. Whatever technology we used in the end, we better start doing something soon, before 100 million bullets become a trillion and the trap is set. If we don't act, our adventure in space might end before it's even begun.